Test, test. Okay. Hello, everybody. We are going to officially get things kicked off to try to keep us on time today. We have a lot of sessions over the next 2 days. So welcome to VeloxCon 2026, both for the folks in the room and on live stream. We're so excited, and it's so awesome to see many of you here. Thank you for being early and on time today. By way of introduction, I am Allie Leclerc. I work on open source at IBM, and I am thrilled to be a part of the VeloxCon committee for yet another year. And I am joined by Akash Deep from Meta. So as we get things kicked off this morning, Akash and I just wanted to take a few minutes to talk about the Velox community, highlight some of the latest work and some of the community going-ons that have been going on for the last year since we met last. And that's what we're really excited to do today. So this event is really about one thing, and it's about how we are advancing AI and SQL analytics through shared infrastructure. And Velox is at the center of that. Over the next 2 days, you're going to hear from tons of engineers, the folks that are actually building this stack across companies, across use cases, and across the entire ecosystem. First of all, though, what a year it's been for the community. Back in December, we hosted our first ever VeloxCon China. I think some of you may have even been there, which was a huge milestone in expanding the community globally. And then in March, Velox showed up on a pretty big stage, NVIDIA GTC, where Jensen gave the work that NVIDIA and IBM is doing with Velox a pretty big shout out. So you'll hear more about all of that work tomorrow, but this was a pretty exciting day for the Velox team and the community around it. So for me, this is all a signal. Velox isn't just some small niche project coming out of Meta anymore. It's showing up in the broader conversations around AI infrastructure. So if you were here last year, you might recognize this slide, but we have some new numbers. So over the last year, since we've met last, we've seen an 80% growth and new contributors. And we've added 115 new contributors in the last year, which is nearly double the previous year. That's pretty incredible. Across the board, stars, forks, commits, they're all growing at a super impressive rate. But the most important thing here is not just the growth, it's the type of growth. And it's signaling that this isn't just passive interest. We're seeing active builders. We're seeing people not just watching, but doing. And we all know Velox started at Meta, but today it's being built by engineers across 30 different organizations. So really awesome to see such growth in these numbers. And of course, who doesn't love a logo wall? Just some examples of both Velox users and contributors to the project. So all really exciting to see. So I'm going to make one more important change then. Velox is not becoming foundational infrastructure. Velox is foundational infrastructure, and these numbers are a testament to that. That's really great. Okay, with that, I'd like to pass it over to Akash to share more about some of the stuff going on in both Velox and Meta.
Yep. Thank you. Thanks, Ali. Yep. So hello, everyone. This is Akash. I am an engineering manager here in the Presto team at Meta. I'm going to talk about some of the community-driven innovations and what we have been up to here at Meta. And also, I'll talk about some of the culture and collaboration. So Velox as an ecosystem is seeing a lot of expansion across multiple dimensions. There is hardware acceleration and hardware innovation which is happening, and Velox is the place where it is meeting query execution. There is work happening on platform adoption side. Different clouds, platforms are adopting Velox as well. In addition, I think there is existing compute engines which are like Presto and Spark, they are also maturing in how they have adopted Velox. There is more maturity in terms of like getting more sophisticated and deeper integration and stuff like that. Yep. So moving on, I want to highlight some of the recent work from the community. So the first one is Presto GPU with UCX Exchange. So here we have enabled multi-GPU and multi-node execution, which unlocks GPU-accelerated query processing at scale. It's a big step towards making Velox a heterogeneous compute engine. Then we also got the full Iceberg V2 read and write support. It brings Iceberg on parity with the Hive performance and makes like the compute engines which Velox support first-class citizen on the Iceberg ecosystem. Next one is we also launched geospatial support along with close partnership with open source. So we are going to hear a lot about many of these over the next few days. Moving on, I want to also take a moment to talk about one of the most important part, which is the community foundation and community support. In the last 6 months alone, we have had 700 plus contributions from the community. It has been across bug fixing, across performance improvement, fixing tests, improvements to the build and CI, and also documentation improvement. It has been coming from across different like companies like IBM, NVIDIA, ARM, Intel, etc. And there are people who have found something which was broken and have fixed it. And I want to say that I think this is what keeps the project going on and makes it like available for others to build on. From there, I want to talk about few milestones here at Meta. Which will show how deeply Velox is integrated at Meta. So we completed the Prestissimo migration last year. Now 100% of Presto workloads at Meta are powered by Velox. The next one is Velox is the default engine which is used for training data loading for new recommendation model. So Velox is no more just the SQL engine. It's also part of the ML training pipeline. And we have also started using Gluten internally, which is bringing Velox into the Spark ecosystem as well. And these three together paint a really key picture that Velox is now a critical part of the infrastructure here at Meta, both in the analytics and AI workload. And we'll have, like, I think, many talks over the next couple of days on these. Moving to the culture and collaboration part on how we build together. So open source is not just about publishing code. It's a culture of collaboration, and I think there is an interesting flywheel which we get out of building in the open. So there are two effects which we didn't fully anticipate. The first one was incentivizing hardware partners to invest more deeply. When the code is public and widely adopted, partners like NVIDIA and ARM, they are able to contribute optimizations directly. And then the second one is a more newer one, which is AI-assisted development becomes a lot easier when the code is available in the open, design docs are in the open, and the RFCs are also available. Next, I'll break it down into three pillars quickly. So first one is we are built in the open with public design docs, with a formalized design philosophy, and we have an open RFC process as well. Like I talked about in the last slide, we have the hardware flywheel, which is going on, where hardware partners are able to contribute optimizations directly. And then the last one is a newer one, which is it's also better for AI because we have open code, open docs, and open RFCs. So moving on to the last one, which is, join us. If you are already using Velox, that's great. If not, use it using, Presto, Spark, or PyVelox. You can contribute through open issues, opening issues, contributing on diffs and join design discussions as well. And then definitely connect, join our Slack or GitHub discussions, and yeah. So yeah, I think with that, I'll give it back to Ali.
Okay, I think I have a few housekeeping items that Meta wanted me to share with folks in the room. So one is, like I mentioned, we are live streaming. So hi to all the live streamers. Great to have you here. And recording all sessions. For those that are non-Meta employees, make sure you bring your badge back tomorrow and you enter through lobby 14, which is where you all hopefully did. You'll do the same thing tomorrow. Just remember to keep your badge and bring it back tomorrow. We do have a conference room available for ad hoc discussions if you need some quiet space to sit and work. It's right across the way. It's called Chips and Salsa. So that room is also ours to use, so feel free to drop in there if you need to. Folks that took a ride share, if you are planning on leaving before 7, you need to take the tram back to the ride share area. If you're going to stay for the party, you can get a ride share from here after 7. And finally, tonight, we hope you stay for the conference party. It seems like it's going to be a really nice day weather-wise, and we are doing it right out here in the garden. So we hope you can stay and hang out and chat with the Velox community. I have to say thank you to the conference committee. These things are quite hard to pull off behind the scenes, and so across Meta, IBM, and NVIDIA, there were a bunch of people who helped put this together. So thank you to all of them for the next 2 days of hopefully really awesome things around Velox. Finally, thank you to all of you. Our community is amazing, whether you've contributed, you've mentored, you reviewed, all of these things. You're the reason why we're seeing such great numbers and why this community works. So thank you. We always like to end with a little what's next. If you remember last year, we said maybe we would be going to China, and we did it. So what's in store for this year? Maybe in a VeloxCon Europe, maybe another VeloxCon China. So stay tuned. Oops. We are really excited for those events and to keep growing the community worldwide. Okay, with that, let's officially kick things off with our first Velox session keynote of the day from Pedro. So Pedro, why don't you come get set up? Thank you.
All right. Yeah, so let's get going. I'm happy to kick off the technical sessions. I'm super happy to be here at VeloxCon, hosting a bunch of people from Meta and the industry. So thanks for joining. So when I put together this talk, I was trying to give an overview about Velox and what's happening, but we're also going to have a lot of talks that will get into more detail. So I tried to take a step back and talk a little bit more kind of high-level workloads, where those workloads are going, some changes that are happening because of AI, and talking about not just Velox, but some of the other components we've been developing, other things that we open source recently. So kind of focus on not just on Velox, but things that are happening around the Velox sort of ecosystem. First, again, just want to thank everyone for taking the time for joining us. I know it kind of takes taking 2 days out of your time is not it's not easy. So thanks for joining. It's great to see so many familiar faces. For those who have not joined every single VeloxCon, the very first VeloxCon was actually held in this room. I'm wearing the T-shirt, so it's kind of nice to be back. I think it was back in 2023. Now we're in the 4th VeloxCon, and like Ali said, we're kind of 5th because we held VeloxCon China, which is kind of a side charter. Hopefully going to do this year again, but thanks everyone for joining. Just kind of how when we started Velox, what the sort of the world and the workloads in a lakehouse look like. So we had what people used to call, or what we call it nowadays, the analytics lakehouse, which is essentially a lakehouse that was built and optimized for analytic workloads, like things for business intelligence and decision making, right? So we had workloads around dashboarding, data exploration, generating reports, kind of slicing and dicing dashboards. Another big use case was A/B test experimentation platforms, right? So people, they want to run experiments at large scale. You change the color of your button, and you want to create large data cubes that let you slice and dice the data and see, is engagement going up or down? So there's a lot of interesting use cases from this analytics lakehouse back maybe 5-6 years ago when we started Velox. If you really take a step back, maybe a 10,000 feet view of this lakehouse, you see essentially there's a shared storage. You have some ingestion pipeline that usually ingests kind of logs from applications and web logs. And there are 2 main workloads. One main workload is just batch, right? So you have this idea of running large-scale pipelines to generate data sets that maybe trigger another pipeline that generate new data sets, right? So just this idea of kind of keep processing and curating the data, data pipelines. That's usually where people use Spark in the industry quite a lot, but of course there are many other tools. Another important use case was just the kind of using this data or taking this data out of the warehouse, right? So just kind of the analytics tool that let you kind of slice and dice the data, power dashboards, and they usually optimize a lot more for latency, right? On the right side, I think for this community, like many people use Presto, like although you can also use Presto for batch, you can also use Spark for interactive workloads to some extent. But those are kind of the main workloads, and when we started Velox, those are the things we focus on. One side was Spark integration, the other side was Presto integration. Fast forwarding to today, we have what we are calling the AI lakehouse, right? Which is essentially kind of the same. But it's a lakehouse that is optimized for AI workloads. So now we're in a world where AI is the biggest consumer, both in terms of data, in terms of compute. That means that most of the data and most of the tables you have on the warehouse, they're actually training tables, like to power training. And most of the compute you have is actually to curate those tables and to feed those tables into trainer, right? So whether we like it or not, AI is the biggest customer, right? So we need to continue relevant. We need to continue sort of optimizing and evolving for this type of workloads. And now instead of 2, we have maybe 3 workloads. So we still have a batch, the ETL, the data preparation, except that it looks slightly different, right? So now for the batch workloads, we now call training data preparation, which is, like I said, most of the batch pipelines are actually preparing data sets for training. People still use a lot of Spark for doing those things, but there's some kind of differences between what you use for training data preparation today and what you used to use for analytics warehouse. One of the main characteristics is that usually training data sets, they're a lot wider. So usually you have a lot of features. Those features sometimes are large maps, and those maps might contain sequences. So the sort of the shape of those tables really change. So just using vanilla Spark or kind of vanilla engines that were developed for analytics back in the day, like is usually not very efficient. One of the main workloads you have on training data preparation is this idea of feature injection, which is when you have your training data set and you calculate a new feature offline, how do you inject this feature in the training data set without having to rewrite the entire table? So this is a very recurrent and very common workload that you need to support very efficiently. So last year we had, actually my talk was a lot focusing on that. I see that Konstantinos is now in the back, and last year he also had a talk about like how to use PySpark to accelerate some of those workloads. So there was a lot of discussions last year about this. And of course, as you're kind of moving data that is really, really wide, you want to make sure that you kind of read and you decode and you transform this data as few times as possible. So if you have things like operations that are cardinality reducing, like filters or joins, like you want to lazy materialize things as much as you can, because materializing data that is really wide is actually super expensive. Right? So there's a lot of tricks on how you push lazy materialization further. We also have this idea of encoding preservation, which is if you're moving a bunch of data from one table to the other, like how can you sort of minimize the amount of transformations that happen to this data? For example, if this data is already really packed and encoded in the source table, can you actually move this to the target table without decoding and without decompressing? So there's a lot of kind of tricks there. If you're interested, we kind of talked about this last year. Right. Second one is the interactive workloads. This is kind of the same, not much different. The main difference is that now, well, as we all know, we don't have as many humans interacting with those things. You're mostly interacting through agents. Query patterns from agents, they're not as different. There's this discussion that we usually have a lot more, right, because those agents are issuing a lot more queries. So there's discussions on how do you cache, how you can potentially pull this data locally so you can enable agents to slice and dice this data locally. So you have a much higher volume of queries. There's also discussions on how to enable kind of more advanced types of analytics, things like vector search, so you can calculate similarities and things like that. There's going to be a bunch of talks. Zichen has a talk about vector search. But I think this is one of the kind of the second workload is just essentially agents looking and transforming and slicing and dicing this data on behalf of humans. But then we also have this third workload is that especially for large-scale warehouses, you're putting this data in the warehouse and you're transforming because you actually want to train large-scale models, right? And this is something that essentially didn't exist before. This has been one of the main focuses of the Velox team in collaboration with the many other infrastructure teams at Meta. And I have a couple of slides to detail and to focus a little bit more on what happens inside this sort of data loading for training. All right, so what's training data loading? So training data load is essentially kind of a compute engine, but the destination is not a table, the destination is not pixels on a dashboard, like the destination are trainers. Trainers are basically programs that usually use libraries like PyTorch or TensorFlow, right? So they ingest batches of data. And you go through this training process that does a bunch of matrix multiplications and things like that, and in the end, you generate a trained model. Right? So essentially, like you're pulling and consuming the data, doing some transformations, and feeding this data into processes that do the actual training of models. It is a compute engine, but it has some particular characteristics. One of the main things that it's a little bit more of a mental model than just kind of specific details of the engine, but the main optimization goal on training data loading engines are the fact that you're optimizing for GPUs. So the main thing you want to optimize for is you want to make sure that GPUs are always fed and you're not starving GPUs because you have very few GPUs and they're expensive, right? So usually some other engines you optimize for efficiency, maybe you optimize for latency, right? Like here, I mean, you also care about those things, but you care a lot more about making sure you have this kind of a fixed stream of data in the GPUs. You have two main use cases for those things nowadays. On one side, you have generative AI, things like LLMs. In this case, you do a lot more of kind of the data cooking, all the preparation happens offline. So like we discussed, like a lot of that stuff happens in Spark during training data preparation. And at training time, usually the transformations you do are a lot simpler and more uniform. On the other hand, when you're training recommendations models, they're usually a lot heavier in terms of pre-processing. Right? So as you are reading this data from the warehouse, you usually do a lot more sort of post-processing or last mile processing before you feed this data into trainers. There's a lot of reasons for that. One of the reasons is that you're usually pulling data from different data sources. Like so sometimes you need to join, kind of stitch data together. There's a lot of workloads on just kind of extracting labels and extracting signals from raw data, which is, we can think as a bunch of kind of lambda functions and expressions that generate a binary label. So a lot of that you want to do as you load data on the trainers because people are doing experimentation and they want to try different things. They want to try one feature, it didn't work, they want to try something else. There's also this process of kind of encoding features. There's a lot of feature engineering, like normalizing things and reducing dimensionality. Usually when you're training recommendation models, you have high cardinality, multi-categorical columns and features. And those things usually require very large embedding tables. They're kind of hard to manage. You cannot just copy them everywhere. You need to shard things. So sometimes you need to shuffle the data. So there's a lot of complications. So usually what you see on the architecture of those systems is that usually when you're training LLMs, you do all this preparation beforehand, and you load data into storage. So when you're training data, you're essentially moving this data from storage directly into trainers. While for recommendation models, you have this data in storage, but as you pull this data for training, you do a lot more pre-processing to a point where those things usually cannot fit on the actual training servers that have GPUs because of what we just said, right? If you have too much workload, if you get bottlenecked on CPU on the trainer, then you're going to be starving GPUs. So the idea is that usually for those systems, you disaggregate compute. So you have this tier of workers between trainers and storage to kind of absorb this kind of high amount of compute. And then, of course, the more models you have, the more data, the more kind of complex those transformations get, the larger this tier gets. Right? So if you look at this kind of tier of compute, it's actually a very substantial part of compute, right? It's actually comparable to the other two workloads we just mentioned, if not larger. So yeah, great. So we need to load data into trainers. Can we just run Presto or can we run Spark? You have table scans, you have filters, you can do merge joins, you can do all those things, and that should just feed to trainers, and you're kind of good. So that's a lot of discussions we had in the beginning, like especially when sort of data people were getting into the space, and it turns out that many things are very similar, but many things are kind of not quite the same. Some of the interesting things here is that when you load data in trainers, Batching really matters. So usually when you're training your model, you have a very specific batch size. Let's say 1,000 training samples, or 2,000, or 4,000. And the batch needs to have the exact same size. Right? So usually when you're processing things inside engines, if you're filtering, if you have joins, you can get batches of all possible sizes and kind of aggregating those things. Like most operations are kind of associative and commutative, so batching doesn't really matter. Like here, it really, really matters. Ordering of the data matters. Depending on the order you feed this data into the trainers, you can get a completely different model with different qualities. So usually you want to specify what's the order of your data, how do you kind of scan different days or different hours in the day, how do you kind of mix this data inside batches. So not just the ordering, but the data mix you have inside those batches really matter. So sometimes you can want to have in the same batch, you want to have data for today and mix with 50% of data from, I don't know, last week. And those things really matter, and like I said, if you don't do that, your model might have very different characteristics. And those are things that you cannot even express in SQL, and they really, really matter here. Synchronization here really, really matters. So the way this thing works is that usually you have a cluster with many, many GPUs. And for every single pass of your training process, you need to fit one batch into one GPU. Once you have all those batches, you do forward pass, you do backward passes, you need to shuffle data in between. So if you have one GPU struggling, or if one batch is delayed, you end up starving the entire cluster or all the GPUs assigned for that job. So synchronization in this case really, really matters, right? So you want to make sure that you have all of your sort of distributed queues optimized so that you make sure that the training process is going without starving GPUs. So all those things are kind of different requirements if you look at how traditional compute engines work. Data completeness in this case doesn't matter as much, right? While when you're running analytic queries, you need to process every single record because you need to guarantee that the results match, right? Because otherwise, maybe, I don't know, your revenue results will be missing $1 million or whatever that is. Here, in some cases, if you drop some data on the floor, it's not that big deal. In many cases, for example, if you don't have a batch with the right size, you rather just throw this batch away than kind of, trying to train with an incomplete batch. Right? So the requirements are kind of slightly different. There's some other kind of particularities that are not very different from compute engines, but also worth calling out. Usually when you're running, especially when you're training large-scale jobs, those large-scale models, those jobs might take quite a while. Right? So it can run for many hours, for many days. And you want to checkpoint those things. If something goes bad, you need to be able to kind of roll out to the last checkpoint. Many compute engines can do checkpoints across stages. Like here would be a single stage, and you need to checkpoint that specific stage. So some engines do that, but it's just something worth calling out. Again, going back to not starving GPUs, depending on how much processing you do on those workers, you might need to scale those things up and down. Right? So you need to make sure you can do this very efficiently to make sure that the stream of data going into the GPUs are kind of uniform. There's also this interesting part that, especially for recommendation models, data freshness really matters because users, things that users like are always changing. So you go to Instagram, you go to whatever application, you like cat videos, next day you like dog videos. And so you need to make sure you have an online way to train and to update the weights of your model. All right, so it's a completely different thing. Do we need a completely different engine? Kind of. So sort of the orchestration, the platform is different, but the processing you do inside those things are very similar. So if you look at how you scan tables, how you push down filters, how you decode files, that's all the same. How you kind of execute expressions, how you express UDFs and filters and joins, like all of that is just the same, right? So while we cannot just use Spark or Presto or whatever engine for training, we can use those components, right? So it just happened that we have this library which kind of extracts that from the engine and lets you use those operations in different contexts. Not going to go too deep into details here. If you're interested in kind of more details of how this platform works and how those things are getting integrated, Elodie has a talk later today. She's probably here somewhere. Stay around. It's a great talk. So what happens inside those workers? Like when you're training, when you're moving this data from the store into the trainers, basically you use Velox or a Velox task to pull this data from out of the warehouse. You decode this data, you do some joins, a filter, and all of that. At some point, you generate Velox vectors, right, which is this way of representing data in memory. You need to convert that into tensors before you pass into the trainer, which is a PyTorch or a TensorFlow process. Oops, dismiss. So what's a tensor, right? So tensor, I think we always joke inside data infra teams that tensor is just some AI jargon to kind of keep data people away. When we started doing those integrations, there was a lot of discussions of like, no, we can't use this, tensors, right? Like kind of, no, something that's supposed to scare you. Of course, there's a nicer mathematical formal description, but in the end of the day, it's a buffer. It's a multidimensional buffer that lets you handle multidimensionality, like has APIs for you to sort of slice and dice dimensions, like do strides and things like that. But in the end of the day, it's just a multidimensional buffer, usually contain scalar numbers, mostly floats, but you can have integers and things like that. It's not like Velox that, or things like Arrow, where you can actually have arrays and maps and, and things like that. Usually, tensor is just a multidimensional buffer of scalar numbers. Well, so sometimes those tensors are really large, right? So you can have many, many dimensions. Like a single tensor might have gigabytes of data. In some other cases, you have tensors that are quite small. They represent a single dimension or a couple of dimensions, right? So kind of there are tensors and tensors. Of course, some of the tensors you use for training, like they're very different and they have very particular characteristics. Some of the tensors you use in this process, they're essentially like something like an arrow buffer or a Velox vector buffer. To transform those things back and forth, usually we have a process that we call feature encoding. So you're pulling this data out of the warehouse, you get this data out of Velox. So to transform this data into a tensor, you have to sort of encode this tensor. There's a lot of questions on how do you do that? What are the different types of tensors you support? How do you configure this operation? So for example, if you're reading like a scalar column with floats, it's kind of easy. What if this column is actually a map? Or what if you have a map with an array inside? Like how do you do those mappings? How do you map those things into tensor dimensions is actually something not super straightforward and not well defined. I would say it's even not defined anywhere. So there's another project on the same sort of Velox ecosystem that we started developing internally called A11, which is something that's supposed to kind of standardize a lot of those conversions between vectors and tensors. It's something that exists, but it was just kind of scattered through a bunch of code bases, like not in a very consistent way. So the idea here is just provide a canonical implementation of feature encoders and canonical implementations of sort of different tensor shapes and tensor layouts. So this basically, it doesn't re-implement the tensors themselves. It's just a library that wraps around PyTorch A10 tensors. A10 is the kind of the internal C or C++ library that handles tensors inside PyTorch. So A10, A11. So in A11, you can have representation of different types of tensor, dense tensors, dense and sparse features. You can have encoding, so you can have tensors representing kind of duplication of things like dictionary encoding. We provide kind of basic batching-related operation. Remember that discussion that batching really, really matters, right? So we can have this sort of semantic layer on top of tensor, and you can still sort of split and concatenate them to sort of give you more flexibility on how you organize your compute. It ships with a feature encoder. Feature encoder, again, there's a discussion that batching really matters. So as you encode data, you can actually specify the size of the batches you want to generate. We're also adding features like encoding preserving. Like in many cases, you're reading this data, and the data is already kind of really packed like as a dictionary. So as you do the feature conversion, you want to sort of maintain this encoding, right? You don't want to unpack this entire thing and then pack it again downstream. All the operations we are adding to A11, they're built based on PyTorch operations, which means that this is sort of portable between CPUs, GPUs, and whatever other accelerators PyTorch supports. So one way to reason about feature encoder is just making a parallel with table writer. So it actually happens, I mean, not exactly the same, but there's a lot of similarities. So when you're encoding features, you have a process that kind of keeps consuming data out of your Velox tasks. You keep consuming, you keep batching until you reach a certain size. You encode this data in some special format, and then once you hit this size, you kind of produce something, right? It just happens that when you're writing tables, you're accumulating vectors until you reach a stripe size, and then you encode things using Parquet streams or C streams or whatever file format you have. You generate a buffer, and then you sort of write that to storage. Here, I mean, kind of the same. You accumulate until you have the batch size. The encoding is using A11 encoders, and then you produce this batch that you pass to the GPU for training. Right? Like the data flow is the same. Another interesting part is if you look at a compute, so of the Velox part, which is sort of stitching data back together, filtering, applying data transformation, is actually just kind of half of the workload. So what happens is you stitch this data together, you use something like A11 or some way to encode those features into tensors. And then there's a lot of processing, a lot of compute that happens in those tensors, which are more kind of numerical transformations, normalizing features, sort of reducing the dimensionality and a bunch of things. Why do those things run into tensors? A lot of reasons, but one of the main reasons is because those transformations are really close to the model, meaning that you need to apply the sort of usually the exact same transformations during training and during inference. And during inference, you don't have like a Velox batches, you have other things. So there's a lot of kind of transformations that happen after the feature encoder process. That if you really look into that, is a bunch of tensor transformations, and they look very sort of AI and sort of exotic. But if you kind of just really what they're doing is basically compute, right? So you can understand that as expression evaluation, kind of the same trade-offs. You have columnar buffers. You can do vectorization. You have virtual dispatches. You can JIT compile. So it's kind of the same. Instead of expressing those things in SQL, you express that in Python using PyTorch. Instead of Velox vectors or arrow arrays, you have tensors, right? But if you kind of remove the noise, it's kind of the same. So there's a discussion that, well, if it's a tensor, just move to the GPU and then we're good with it, which is something we're working on. The idea is that, well, not quite, like we discussed in the other slide, there are many, many types of tensors. If you have really large tensors and very kind of chunky operations, it's great. You submit your CUDA kernel and you're great. If those operations are over small batches and they're actually quite cheap, kind of just mapping this to CUDA kernel is not efficient, right? So there's a lot of discussions on how do you map and how do you pack those things. Just happens that we took a head start on those things with the Velox wave a couple of years ago. I don't know if I think Ori is not here yet. So now there's a lot of discussions on what can we reuse from Velox wave, right? This idea of doing that for sort of expression evaluation and query processing in Velox. And how can we map this into sort of tensors and PyTorch? So Ori has a talk tomorrow that's going to give you all the details about this thing. All right. There's a bunch of stuff we're doing around compute. We have those three main workloads. What about storage? Like, is the storage the same? Are there new features? So it also turns out that the way you store this data is also not very efficient if you just use traditional sort of storage and file formats and table layouts that were developed for analytics. Like I said, the data is usually much wider. You usually have many, many features. In many cases, because you want to add features and remove features very frequently, you don't map those features as top-level columns, right? You just kind of plumb all of them inside maps. There's a bunch of discussions on how do you support maps efficiently, how can you sort of project individual features very efficiently from maps. So we ended up creating this new sort of mapping encoding called flat maps. There's a discussion that sometimes those features actually very long sequences of user interactions, and sort of the longer those interactions, the better, right? So the data is really, really wide. There's also discussions that there's a lot of transformations that happen during this training data loading process that could be potentially cached. So if you want to cache or if you want to materialize, how do you map different tensor types to file formats? So there's a lot of kind of interesting questions on the storage layout here. A few years ago, we created this new file format called Nimble. It has a few interesting characteristics. It has this idea of supporting cascading encodings, right? Which is it can take an encoded stream and then put another encoded inside another encoded stream, and you can do those things hierarchically. It's very interesting because it lets you do encoding over kind of nested structures, right? So you can take entire vectors or entire maps and you can deduplicate them, right? If you can kind of cascade those things. So it supports cascading encodings. There's also this idea that because AI is growing so fast, like we're probably going to come up with kind of different ways to encode streams on disk, right? So like just making sure that the way you build encodings inside file formats is extensible. Because, again, this thing is really, really wide and denormalized. It just goes up to a point, right? You're going to get to a point where you can only fit a single row inside a stripe or in memory, and then, none of the vectorization things make a lot more sense. So, of course, there's a lot of interest in how can we actually normalize those things so we can kind of move the bulk of features somewhere else, make the training tables skinnier, and then, of course, you need to normalize. You need to join them and stitch them back together on the fly. There's a lot of discussions on like how do you support this in file formats. We ended up adding support for dense and now cluster and now dense indices in Nimble. There's a discussion that when you have indices on the file, how do you stitch them back together? So in Velox, we ended up also adding support for things like index lookup joins and index table scans. There's a lot of new features we're exploring inside Nimble, like we discussed, how do you map tensors, what are the tensor types, how do you encode those things, how can you potentially have indices for vector search and things like that. So if you're interested in this space, we're going to have a talk later today by our very own Mang, who's kind of a famous engineer superstar. After VeloxCon, we realized that he's a super famous engineer. He's I don't know if he's here yet, but he's going to tell you all about storage, what's happening on the file format layer, what's happening on the table on the table layer, things like iceberg support, Pymon support, and things like that. All right, the last thing I want to quickly talk about is front end. So we're getting to a point where looking at the three main workloads, which kind of cover the bulk of compute, all of that is converging to Velox. It has already converged, like Akash mentioned earlier today, from the sort of interactive analytics, all the Presto workload is already running on Velox. We're now converging in Spark, we're converging training. So what's next? So a few years ago, I think it was 2023, we put together this vision paper. We published that at VLDB, which is this idea of like a vision paper that you should actually look at those monolithic compute engines and you should decompose them into components so that it would give you a lot more flexibility in kind of reusing those components. You can reuse them, it improves engineering efficiency. We don't need to re-implement the same things over and over. So we actually made a lot of progress on that. So this was sort of the kind of the data stack we proposed on that vision paper. Of course, this is a lot more from a query processing perspective, right? But you have a language, you have sort of a way to represent queries, like this IR or logical plan and physical plans. You have optimizers, execution, and runtime, which is sort of the environment where you run those things. We're getting to a point where we were able to converge execution and Velox. So I think not just internally, but if you look across the industry, like, Velox is becoming pretty pervasive. Right? So this part is good, but what we ended up seeing is that if you look at the front end, and by front end we mean sort of the language layer, the optimizer, and the IR, we kind of have similar problems. So there's a lot of things that we end up re-implementing, like for example, things like if you need support for Pymon or for Iceberg, you need to sort of implement the metadata layer on every single engine. If you now need support for indices and index lookup joins, you need to extend every single optimizer. So there's a lot of kind of duplication of work as this part that maybe is similar features in different systems. They are kind of inconsistent. They don't act in the exact same way. Some systems have features that are not available in the others, and then for users, it's really hard to reason about. The other big problem with this is that language is, or kind of the way we develop compute engines is that language is coupled with execution. So it means that usually if you want to use Spark, you need to write things using Spark SQL or whatever Spark dialect or PySpark. If you want to run things in Presto, you need to use Presto SQL. So usually if you want to use a specific engine, you need to write or you need to rewrite your query using that specific engine dialect and semantic, which is, not great. So there's no very good reason to do so. Like if you look at execution perspective, runtime, there's really nothing particular or no good reason why that should be kind of tightly coupled with the language layer. So what do we do? What's the answer? Well, we're going to compose the front end as well. So we're getting to this. So we started this project called Axiom a couple of years ago. It has a language layer. It has an optimizer. We support Presto SQL, Spark SQL. We also recently added a new Spark Connect implementation that supports PySpark on the same stack. We call that collagen, if you understand why it's called, what's named after protein. But yeah, so there's this new stack called Axiom. Has a lot of benefits, better reusability, engineering efficiency. It lets you support many languages. We can build the exact same stack and reuse for multiple languages and multiple dialects. And this idea of sort of decoupling language and execution. Not going to give you too many details. The very next keynote by Masha, she's going to give you all the details and talk about where we are, what's the vision, what's the architecture, and how we're making progress. All of this is also open source. So just wrapping up, of course, data is more critical than ever. There's no AI without data. You need data to train your models. You need data for agents, right? So not just data, but we also need very efficient ways to kind of continue processing this data. So our experience is that composable data systems, they have been really helping, right? A lot of the things you do inside the engine are the same, but the way you put those engines together, they're usually very particular to the use case. Right? So this is something that over the years we saw that was really kind of the best or the winning architecture, like just looking at common components, extracting them out, making sure they're really high quality, they're very efficient, and reusing across engines. collaborating with the open source community, making sure all those things are open source, working with other companies that has been also super helpful. We intend to do more of that. Of course, the main project was Velox, but we're also making some good progress with Nimble, now with Axiom, Collagen, Velox Wave, A11. It's not open source yet, but we have plans to open source it later this year. So this has kind of been the winning strategy. So yeah, thanks everyone for listening. At Meta, we usually like to end things with this journey is 1% done to give this idea. There's always a lot more going on. Thanks for joining and hope you enjoyed the program. Thank you.
While Masha's getting set up, we did not leave a ton of time for questions, so all presenters will go make themselves available during breaks, so just feel free to grab folks if you have questions, and you can have discussions in the hall. Okay, so with that, I am so excited to introduce Masha, one of the co-creators of Velox, to give the second keynote of the morning on Axiom. So Masha, I will pass you the mic.
Thank you so much. Welcome, everybody. Give us a few seconds to set up, and we'll begin shortly. Thank you so much for helping us set up. I think we're good to go and get started. I'm Masha, and today I'll be talking about Axiom, a composable C++ framework for building query engines on top of Velox. If you take one thing away from this talk, let it be this. Velox made execution composable. Axiom extends that to the full stack: parsing, analysis, optimization, and runtime. By the end of the talk, I'd like you to ask, can my engine be built on this? So what do we mean by composable? Think of Axiom as Lego for query processing. You have a set of reusable pieces, an API, optimizer, runtime, and you can snap them together in different ways to build different engines. The pieces are compatible, but they don't restrict how you put them together. You can swap components, extend them, or replace entirely. The key insight is that these pieces shouldn't have to be rebuilt for every new engine. Today they are, and teams spend significant time building a foundation that looks much like everyone else's before they get to the unique value their engine was meant to deliver. Axiom lets you skip that and start where it matters. For existing engines, rebuilding on a composable foundation unlocks new deployment modes and APIs. The same engine can run embedded on a laptop or distributed across a cluster with streaming or durable shuffle, and offer both SQL and data frame APIs. That's the vision. And if it sounds familiar, it should. It's the same vision that drove Velox, extended to the full stack. Velox provided a reusable library of efficient operators and allowed teams to rebuild the execution layer of Presto through Prestissima and Spark through Gluten on a shared foundation, delivering 2 to 3x efficiency gains across the board. Data processing for AI training pipelines was also rebuilt on Velox, gaining not just efficiency, but reliability and functionality that had originally been built for Presto and Spark. That's the power of a shared library. Every engine benefits from every other engine's investments. And because the operator library is shared, IBM and NVIDIA can build GPU-native implementations once, and any engine built on Velox can adopt them. That's a remarkable success story. But here's the thing. Velox solved composability for execution layer. But everything above, parsing, optimization, coordination, remains monolithic and engine-specific. Each engine has its own full stack above Velox, and those stacks don't share anything. That's the gap we set out to fill. But before we show you how, let's look at why this matters for users and developers. Real-world data workflows don't fit neatly into one engine. You might start with a streaming pipeline, run batch transformations, prepare training data for AI models, build interactive dashboards, and debug issues along the way with ad hoc queries. Today, each of those steps uses a different engine. Some with SQL, some with Python data frame APIs, all with different semantics, different tools. And the logic across those steps often overlaps. So inconsistencies between engines don't just slow you down, they cause real bugs. Then possible users try to stick to one engine. Presto can handle both interactive and batch workloads, so most teams start there. But inevitably, data volumes grow. Queries that used to work fine start hitting memory limits or running so long that reliability suffers. The workaround of stretching Presto beyond its sweet spot breaks at the worst possible time, and suddenly you're facing a rewrite in Spark SQL. This problem is so real that we built Sapphire, Presto on Spark, specifically to let users run Presto on Spark runtime without modifying the queries. That's inherently awkward. We are bolting one engine onto another. And neither Presto nor Spark gives you a practical local development experience. Want to lint your SQL or test your logic against sample data? You need a cluster round trip every single time. That's the user side. Now, the developer side is not much better. The architectures are split along language boundaries. In Prestissimo, Java handles SQL parsing, optimization, orchestrates distributed execution. C++ handles local execution through Velox. They talk over RPC, which is relatively clean, but connectors are split. Metadata lives in Java, data reading in C++. Constant folding is a real pain. It has to happen on coordinator in Java, but produce results consistent with Velox execution. Right now, that's solved with a C++ sidecar, which works, but somewhat clunky. Gluten has a similar split. Spark handles parsing, data frame API, optimization, distributed execution, all in Java. Velox handles local execution. They talk over GNI, which is more complex and harder to debug. Both coordinators are monolithic. You can't add data frame API to Presto. Can't run Spark SQL on Presto coordinator or Presto SQL on Spark. You are locked in. So if the problems are clear and the need is real, why hasn't anyone built a unified C++ stack before? We believe the major blocker has been the lack of a reusable C++ query optimizer. Optimizers are extremely hard to build, even with AI. The closest thing to a reusable optimizer in the industry is Catalyst, and it's widely adopted, but it is Java. So when Velox came along, the natural path was to plug it into existing JVM coordinators. Building a C++ optimizer from scratch just wasn't a realistic alternative until now. Axiom is that missing optimizer and more. Let me walk you through the architecture. It comes down to composable components connected by stable contracts. At the top, you have the front ends. Each one, Presto SQL, Spark SQL, PySpark Data Frame API, has its own parser and analyzer. They are independent components, but they all produce the same thing, a dialect-agnostic logical plan. That's the first contract. The logical plan describes what the query does, not how to execute it. It is deliberately compact. A single logical join node says what to join. The optimizer decides how. Hash, merge, index, nested loop. Any front end that produces a valid logical plan can use the same optimizer and the same execution stack. That's what makes it practical to add a Spark SQL parser or a PySpark data frame API without touching the rest of the system. The logical plan feeds into a cost-based optimizer, which produces a physical plan targeting Velox operators. That's the second contract. The physical plan goes to a runtime. Axiom ships with a local runner for embedded single process execution. Axel, which I'll get to shortly, is a distributed runtime built on Axiom. And you could build a streaming runtime on the same foundation. Now, I said the optimizer is the hardest piece. Let me show you why building it in C++ right next to Velox makes the difference. The optimizer directly uses Velox's function registry and expression evaluation, making Velox the single source of truth. No more ensuring that Java's function registry matches exactly, which has been a source of bugs. Constant folding uses the same code path as query execution. No sidecar, no integration overhead. The optimizer can even constant fold scalar subqueries by executing them in process. The optimizer targets Velox operators directly. For example, when planning in or exist subqueries, it uses the semi-filter join operator. Then planning except all counting join. Both are specialized Velox operators that Presto's optimizer is not aware of. It plans a sequence of more generic ones that have to be squashed together in the Presto to Velox translation layer. Building the optimizer in C++ right next to Velox eliminates an entire class of integration problems. Beyond the optimizer, a query engine needs to parallelize work and orchestrate data access. That's where connectors and the runtime come in. Connectors in Axiom are unified. Planning time logic, metadata, statistics, partition pruning, and execution time logic, data reading, both parts are in C++, so they interoperate naturally. In Prustism and Gluten, those are split across Java and C++. The optimizer produces a physical plan, a set of Velox plan fragments connected by shuffle boundaries. The deployment topology is an input to the optimizer, so shuffle costs affect join ordering and other plan decisions. The runtime takes the physical plan and orchestrates execution, embedded in a single process, distributed with streaming or durable shuffle. The user experience stays the same. Same SQL or data frame API, same semantics, regardless of the deployment mode. No query rewrite, no migration. You literally iterate locally using SQL or Python, and then ready, run at scale on a cluster. That's the architecture, and we've talked about this before. This time, we're building it and have early results to share. All TPCH queries work end-to-end, producing optimal plans. We're actively migrating production workloads at Meta. Optimizer and execution stack are handling real queries at scale, not just the benchmarks. Axiom includes an interactive CLI that lets you run SQL locally against TPCH data, local Hive, in-memory data. This has become a popular tool internally. People love sub-second SQL linting and validation without waiting for a cluster round trip. We're also extending Presto SQL with user-friendly features inspired by DuckDB, from first syntax, trailing commas, method call chaining. We're committed to continuing to modernize the language to make it easier to use. That's Axiom's foundation. Let me show you how it extends to distributed execution. Axel is a distributed query engine built entirely on C++, on Axiom and Velox. Reuses everything I just described, the parser, the optimizer, the connectors, and adds the pieces we need for distributed execution. Admission control at the entry point, a distributed scheduler, and Velox workers. The key point is what the Axel team didn't have to build. The team didn't write a parser, didn't write an optimizer, didn't build connectors. All of that came from Axiom. The team focused on the distributed coordination layer, scheduling, fault tolerance, resource management. That's the composability promise in action. Axel currently uses streaming shuffle, targeting interactive workloads, the same space as Prustissima. We're adding durable shuffle to support batch with fault tolerance that Spark users expect. We're still early in the journey, 1%, 0.1%, whatever your single-digit number of choice. But we've seen a lot of excitement and enthusiasm around Axiom across Meta. As we build it out, we are learning that first, the architecture works beyond our original use case. The Graph Query team built a Cypher front-end on top of Axiom. They produce Axiom's logical plan and use the optimizer's cost-based join reordering for graph pattern matching. The logical plan and optimizer work for non-SQL languages as well. Both the streaming and AI training data processing teams adopted Axiom's Press-to-SQL parser to offer a SQL interface alongside their existing Python data frame APIs. Second, users love local sub-second SQL linting and testing. Being able to validate your query instantly without a cluster round trip changes how people work. Third, composable architecture demands crisp contracts between components. It's harder to build than an analytics system, but that discipline pays off in extensibility, reuse, and ability to evolve components independently. What's next? Still a lot to build. Spark SQL parser, PySpark data frame API, closing the gap between Presto Spark users, making optimizer truly extensible, adding index, merge joins, durable shuffle for batch workload with fault tolerance, and the connector ecosystem is ready to grow. Velox made execution composable and delivered massive efficiency gains. Axiom extends that same vision to the full query processing stacks. The pieces are there. Come help us put them together. Any questions if we have a moment?
Thank you, Masha.
Thank you.
Okay, so we are in break now. We have, I think, about, let's see, our next session is at 10:40. So we have just under half an hour. A few notes. One is we are welcome to use the micro kitchen next door. Just don't everybody go take everything all at once. We should also have maybe some stuff out as well, but we are welcome to that. So we'll be back here at 10:40. All right, thanks. Test, test. Oh. All right, we're gonna ask folks to take their seats so that we can keep this thing moving. Okay, so I am happy to introduce Volkmar from IBM, who's going to be sharing more about what we are doing with Velox at IBM. So we're going to get started now, folks. Thanks.
All right. Thanks for attending. I will give an update of what we are doing at IBM in What's Next Data with Velox. Updates from last year to this year, and then where we are heading. Let me see. Okay, wonderful. All right. So we are having a vision how lake houses work in the enterprise. And we believe that it's not a closed box which owns all your data, and it's a black hole you store it in, and then you will never get it out. We think that with open formats, open engines, there is an ecosystem which new software development, as it happens, should be able to leverage. We just heard like 2 talks before. You know, there's AI training directly working with Velox against data sets. And we want to support that type of workloads in our ecosystem. So our goal is to have a very open environment. But then on the flip side, we as IBM, we are serving customers which are in highly regulated industries. So we have this kind of challenge of, on one hand, we want to have open formats, and then you want row-level access controls. And sometimes those things don't work easily together. So we are building an environment where we can support these different workloads while we can preserve the enterprise requirements of the banking industry, insurance industry, governments, etc. Okay, so we have a stack where we believe that stack can actually solve this. So at the bottom, we have our basic infrastructure. We are targeting both cloud and on-premise. This is simply where our customers are. We are seeing a lot of workloads which are in the cloud. There's a lot of data in the cloud. About 80% of data warehousing happens in the cloud. But then the other 20% is usually organizations which are very security sensitive or even sovereign, where they're saying we cannot have something in any of the clouds. We want to have it on premise. Then we are supporting a wide array of storage. We have our own storage systems, and I will talk about this in a second. We are doing deep integration with our storage systems because we believe we can actually get additional performance out by doing a deeper integration, knowing how the data travels between the storage system and the compute systems. One of the examples is GPU Direct. And then we build on these open source data formats, and that's not only the warehouse reading those data sets, but we also have the integration in our own data systems to write them. So for example, DB2 on the mainframe natively supports Parquet files, so data can be directly placed from a transactional system into a lakehouse and become directly accessible. Then we have a unified metadata and governance layer. And so we have a catalog which understands where your data lives. And that catalog has compliance or allows to implement compliance, which is adequate for example, FedRAMP. And then on top, we have these execution engines. And so the execution engines, we believe that there is not one engine which rules them all. But what we are seeing now is that the world is progressing towards highly specialized engines. So on the query layer SQL side, we support Spark and Presto, which is built then on Velox. But then we also have vector databases, OpenSearch, RAG integration with OpenRAG. And then we have all kinds of engines which we have collected over the years. We have Mongo, DataStax, all those engines live side by side, and we are integrating them into a common catalog so that whatever workload you have, you can actually access them to a common control plane, common access controls, but then you pick the engine you want. So Velox is really interesting for us because it is actually a unified execution engine, and now we can start looking at global resource management. And if you look at a normal cluster in production environments, I'm sure Meta has that problem as well. There's a lot of resources sitting around idle. And the more engines you have, the more stranded resources you have. And so those stranded resources become extremely expensive. In particular, when you have, you want short response times, you just keep these systems up and you're bleeding cash. Right? And so one of the goals we have is to unify this as much as we can and actually make it dynamic so that we can have better workload optimization and we can bring down the cost for the customers. Okay, so on the left side, so hybrid and multi-cloud, open by design. We are open source compatible. We want to make sure that any of the open source software or any software which has been written for the open source versions works. We add data security governance. It is really that's where we are investing very heavily to make sure we can bring the technology into the enterprise, really optimizing on price performance, and we are also AI ready. So these systems allow us to curate data which can go in vector databases, and we also have vector stores on the side. So that vision, unifying everything, works on Velox, and it's all built on Velox. We are heavily contributing. On top, we see Presto, Spark with Gluten, Presto with Prestissimo using Velox. And then we are targeting the standard open formats, Icebrook and Parquet. But when we go into enterprise settings, in many cases, we find a barrage of different data formats. And so there's also investment in the Delta Lake, et cetera. All right. So what we are seeing right now is there's a shift in the industry where it used to be, there's an x86 box sitting somewhere in a data center, and it's, you have racks and racks of them, and this was the Google scale-out architecture. And I think we are going through, I don't know how many cycle of this, and we are seeing a shift towards a wider variety of systems. And from our perspective, we are encountering them everywhere. We are encountering cloud environments with x86 boxes, but then also we have customers who have higher reliability requirements, so we are putting power systems in. But then on the flip side, all the cloud providers are now bringing ARM processors into their offerings. And so what we are looking for is, can we enable those types of hardware as well? And then probably the most important and the biggest shift for us right now is NVIDIA, with GPUs becoming widely available. So we are still in the build-out phase where we are adding more GPUs per year than we are removing. So we are not going through a replacement cycle yet, but we are still in that on-ramp where capacity gets massively deployed. But we are already going through that phase where you get the GB300s, and then the H100s are old. And that old allows us, and then you have the 8100s, and so there's a shift down in the cloud providers where hardware, which has been really hot last year, is not that hot anymore. And that's actually if you look at the price performance we can get out of that hardware, it's actually very beneficial for SQL. And so we are targeting those types of platforms, and we are doing a pretty big investment into making these GPUs work well. So this is a quick benchmark. This was run, 2 days ago or so. We took one of our training clusters with H100s, grabbed the machine, and then ran Velox. This is Velox proper, not on Presto, but just Velox itself. Ran the TPC-H benchmark, and then and used 48 cores. This is the machine we just have. You get about 114 seconds to run it. You take the same thing, you run it on a single H100, so the machine has 8, and you get this down to 23 seconds. So we get a 5x performance improvement from a fully utilized x86 box to one H100, not all 8. So there are more in the system. So now, what's the problem? The problem is that we suddenly are in a world where all the numbers you know shift. Right? So if you take an x86 box, you usually have like 2 sockets, somewhere between 600 to 800 gigabytes of memory bandwidth. You have QPI in the middle, you get 100 gigabytes over QPI. And now you are sticking a bunch of GPUs in, and those things have 3.3 terabytes of memory bandwidth. If you go to the B300s, you get like 8 terabytes. And so suddenly you're getting an order of magnitude improve or speed up of the memory bandwidth. But now you don't only have one H100, you have 8. Or B300s, you have 8 of them in the system. So if you look at the ratios, they are all out of whack. Right? So if you think an x86 box, you have, let's say you're well connected, you have a 200 gigabit link, so you get 25 gigabytes into that machine, but you get 26 terabytes per second in memory bandwidth of the GPUs. So you have 1,000x disadvantage or 1,000x extra memory bandwidth. So the big question now is, if you're on a lake house, how do you get that data into the system? And that really, the storage system becomes your bottleneck. And so we are looking at how do we need to re-architect that scale-out system when we are in a scale-up environment. And that actually requires some substantial changes to the system. So we are working together with NVIDIA, someone from NVIDIA I think sits over there, and we are trying to redefine what the reference architecture needs to be. So we have our storage systems. The storage systems support direct GPU direct, so we can actually load data directly from the storage system into the GPU, so we can feed it. And so now, instead of going through the slow 200 gigabit link on the back end, the north-south network, we are going through the training network, which is 3.2 terabytes. So we are effectively bumping the I/O bandwidth by a factor of 10. So now we can feed at least a little bit better, so we are not like totally off. We are still off, but we are not totally off. And then we are looking at how you can leverage on anything which on board can store data so that we get the bandwidth up, so that we can keep the GPUs busy. Hello? Okay. So at the last GTC, Jensen announced, this was faster than we expected, announced that we are working on this together. We have a customer which was on stage, which is Nestle. So Nestle has been working with IBM on running workloads. They have a very large data warehouse, and they have a throughput problem. So they want to take all their order to cache data, which is in their warehouse, and then on a regular basis process it. It takes usually 15 minutes. And on a 2-node A100, they could bring this down to 3 minutes. So it's a massive improvement for them, right? Because they are now they can make decisions on a much faster rate. And so we got the performance or the latency down, but also the system is much more efficient. So they see an 83% cost saving over a normal CPU-based system. So we're getting both. We get a faster system and we get a cheaper execution. So now from an economics perspective, really matters because now you can make decisions faster on that data and you can refresh it more frequently. Okay, so what happened since last VeloxCon? We said we are going to do a bunch of work, and we see Velox really as our core engine. So the what's next data ships with Velox, and over the last year we started doing adding more capabilities and kind of completing what is required to run this in production environments. So one is the Iceberg integration. This Iceberg 2 was complete. Then custom UDF support was really critical. So we see this a lot in enterprises, and we also need to figure out what's a good story for existing UDFs in particular when they are written in Java. So we need to figure out like a long-term strategy so that the deployment becomes easier. Then we are in the middle of re-architecting the partition output, and then top-end row number was delivered. Now, where are we focusing today? So a lot of focus is obviously on the GPU acceleration. then we see Velox as our primary engine for both Presto and Spark. So we are all in. We are working on Iceberg v3 deletion support, deletion vector support. And that's really required because this is just the workloads we are seeing in production environments. You need to have a mutable engine, and the performance improvements we see or we expect from Iceberg v3 are quite tremendous. We also want to make sure that we support Delta Lake because we are meeting data in the wild. We don't necessarily have control over it. And so we need to have support for all data as we find it. Delta Lake is one of the most common file formats which we are seeing with customers. Then there is a bunch of missing functions for SQL completeness. It's on like Presto, for example. There's a big chart and it says which ones are missing. So we want to make sure that we have 100% coverage. And then with this shift towards GPU focus, we are kind of resetting. So we want to make sure that we have full coverage. So TPC-H right now is done. So we can run TPC-H exclusively on GPUs. TPC-DS, we still have a couple of missing functions, around 6. And I think we are at 68% coverage right now. So this is just a question of time. So we want to get to completion. But that doesn't mean that we have SQL completion. It just means that the subset, which is in TPC-H and DS, we have covered. But at least it's a good starting point, and then we will just do the long tail. All right. So I think, I have 2 more minutes. Good. So our vision is we are, as watsonx, this is the product we are shipping. We are open at the core. We powered by Presto C++, Velox, and Gluten. We are targeting hybrid and multi-cloud. We support pretty much every file system we find. We have a strong integration with our own storage systems to make sure that we achieve the performance. Analytics and AI ready. So these engines are driving a lot of the AI workloads we are seeing and the ML workloads. We are offering something which is enterprise ready. Performance is out of the box excellent and it integrates with your existing systems. And security, we have FedRAMP qualification. And so this is really critical in high security environments. As I said, we are really committed. We have 20 project committers right now and 96 project contributors across the family of Velox, Presto, Gluten, and Spark. We are all into this, and it's really nice to meet you here all, and I'm happy to chat. We want to make sure that the community flourishes, and we are really thankful for all the work Meta is doing in this. And go to our web pages, and let's talk. Okay? Thank you.
Okay, I will introduce our next speakers. We have Fei Long and Sebastiano, both from Meta, talking about flexible function registration and execution in Prestissimo.
Hi, everyone. Thank you for coming to the talk. So I'm Fei Long. So today with my colleague Sebastiano, we're going to talk about how we support the Python IA function in Prestissimo. So this is the agenda for today. I'm going to cover the context, the function registration, and my colleague Sebastiano is going to cover the Python runtime, use case, and learning and future work, and we're going to take some QA in the end. So context. What do we want to achieve like in here? So we want to add like a native Python and AI functions in Presto. So the most straightforward way to do this is to add like one UDF for each Python or AI function we want to support. However, this means that we need to do CPP code change for each new function. And also, because the code lives in the Velox and Presto code base, the availability of the function will depend on the Presto release cycle. But we don't want to do this. We want to have it in a flexible way. So we don't want to have any new CPP UDF for the new Presto or AI function. And also, we want to do pure Python code authoring for the new functions. We also want to decouple the availability of the function from the Presto release cycle. The function should be available immediately after the code being merged. And most importantly, so even with this flexibility, we still want it to be easy to use. User should be able to use the function like other regular Presto functions without any overhead over on the user side. And this is how we achieve this. So on the left side, we have an external file system, which have two types of configs. The first one is a function registration config, which includes the functions we want to support and their signature. The second type of configs is a Python script config, which includes the Python script we want to evaluate for the user-defined AI or Python functions. On the Presto side, in the coordinator, we have function namespace manager, which reads the function registration config to register the user-defined functions. On the worker side, we have the Velox UDF, which can execute arbitrary Python script for evaluation. And this UDF is going to execute the Python script config. And we have one function rewriter in the coordinator to rewrite the user-defined function into the Velox UDF. By having all the configs in the external file system, user only need to add it in the file system if they want to support new AI or Python function, or they want to add the existing functions. So by doing this, we achieve the decoupling of the function from the Presto code base. And I'm going to talk about in more detail about the function registration and rewrite. So we use the JSON file-based function namespace manager available in open source with some slight change to do the function registration. The left side shows the snippet of the function registration config. It has the function name, return type, and input types of the function user defined. It also has the one additional Python UDF script field, which points to the Python script that's going to be evaluated for this specific function. On the right side, we show a sample Python script. Here, because we serialize the data into JSON to pass to the UDF for evaluation, we first deserialize the data, then we process it in Python. However, how do we connect the user-defined function and the Velox UDF? Because in the user-defined function, it can have arbitrary number of arguments, with each argument to have arbitrary type. And the return type can also be any type for the user-defined functions. But we want to rewrite this into the Velox UDF, which currently only take 2 arguments, and with each argument to be virtual type. The first one to be the Python script, and second one is a JSON serialized input. And the return type is also a JSON string. And this, on the right side, is the algorithm of how we use the function rewriter to rewrite this. So first, for each function argument, we are going to normalize it into varchar for the user-defined function. Then we pack these arguments into a single JSON array and pass it to the Velox UDF for evaluation. After getting the result, we are to cast the result back to the original type and return to the user. And this is an example of the before and after of the rewrite. So before the rewrite, we are calling the call coefficient function on two arrays. And after the rewrite, we are casting it into a JSON and then pass it to the Velox UDF and then cast the result back to the original type and return to the user. So this is how we do the rewrite on the calling this side. Now I'm going to hand it to my colleague Sebastiano to cover the Python runtime and the next few agenda.
Thanks, Feilong. So as Feilong explained the function registration, I'm going to explain how we actually execute these functions and the Python runtime. So Python DFs here are basically vector functions that are processing batch of rows. And we do this in two different modes. A remote mode, where we do some batch RPC to a remote Python coprocessor service, and also a local mode, where we do actually in-process execution for faster execution. Let's look at the details here. Why remote execution, first of all? Of course, this is to execute untrusted code, so generic user scripts. Also scripts that depend on some heavy dependencies, so library that cannot ship with the core engine, and for isolation, of course. So in this case, we do, so each batch is forwarded via a thrift RPC. And we have one RPC per batch, so this is not one RPC per row. And the Python coprocessor here compiles the scripts, caches the scripts, and also execute the script statement by statement. Since for the backend, this is a black box script, so we need to understand where the result is to return the result to the user. On the other hand, we also have a local execution mode. This is more interesting for, we call it vetted function, vetted script, validated code, can be executed quickly in process. And how do we do this? We do this by using PyBind to manage the C++ Python bindings. We opted for this mode because we have basically zero inter-process communication overheads. It is simple, no additional processes to manage. And this can be done in a fairly simple way. So the life cycle here is that a worker, a Presto worker on a startup can actually instantiate the interpreter and release the GIL, the global interpreter lock, right away. There is a bit of management of the lock here that needs to be done. And from there, workers can run normally, as usual. Then on a UDF call for Python, we have to acquire the global lock, execute Python, then release. Now, since I'm talking lock here, you might think that actually workers are serialized on a lock here. Actually, no. The acquisition release needs to be done in terms of calls, but with free-threaded Python that we use here, this is almost a zero cost so there is no real lock acquisition, and the workers can just go with true parallelism executing the Python. Let me talk about a bit of the problems we had when implementing this. Actually, it is very easy to get it wrong. So we first tried a naive implementation here, where we tried to execute, like in the remote coprocessor, statement by statement, row by row. And the problem here is that this way you get a lot of C++ Python boundary crossings. And this can get very, very slow. Actually, this way, a local execution might be even slower than a remote one. So we provide here a set of guidelines, something that we learn while doing this. So the first one, kind of trivial, is that, of course, the code needs to be compiled as single core object. And if we need to identify the result, this needs to be done at compile time to capture the result statement. The second thing is that executing a script, a black box script, is a bit more expensive than actually calling a function. So this, what we do automatically is wrapping the script in a function and calling the function. The third thing, even that provides even more efficiency here, is when we need to process rows, we need to loop over the batch of rows. It's extremely inefficient to do this in C++, so each time crossing the boundary and sending the input to Python. So this needs to be done entirely in a Python executor, and this way we can cross the boundary once per batch. Is this really worth it, actually? We tried this with a set of micro benchmark. One representative of a more expensive Python execution with regular expressions, string substitution, and one representative of a more lightweight Python execution doing NumPy median on arrays. And we can see here that actually the local execution really pays off, getting as high as 40-45x speed up over a remote execution. This is very ideal for quick execution of functions in process. And of course, the largest, we have large speed up when the serialization payload for the remote execution is larger relative to the computation. There is also a lot of stability here when we execute this locally compared to the remote one. How do we really use this in production? Two main use cases. The first one is built-in Python functions. We ship a set of Python catalogs here for users to use these functions like they are native. So NumPy functions, regular expression, datetime, SciPy, and so on. And from, you can see in this example, the user can just call this as a regular native functions here, just typing py.numpy.median. We are just calling this built-in Python function, so using the mechanism I just explained. And here, depending on how the functions are registered, so using the registration that Feilong explained, the framework can decide whether sending an heavier function remotely, like for instance, a regular expression, or locally, like the median here in this case. The second use case is for AI functions. So a lot of LLM services, inference services, they ship their own Python client. And this is ideal executing the Python client on top of this Python runtime as a Python function. And this is, I mean, kind of a toy example here, but just to show how it works. We have a select queries here, and we call meta.ai.query, so calling the inference service right from the query SQL. Here asking to explain what this SQL does. So we provide a prompt and SQL as inputs, and we get the result, of course, of the explanation of the query. What do we learn from this when using this in production? Two things. One thing on the user experience side, this is really nice because empowers data scientists, ML engineers that are very familiar with Python to implement their own custom logic without really relying on C++ expertise, on Presto engineers expertise, and so on. This is also an agile iteration because we can bypass this way the C++ compilation, and also this also reduces the time to production. And this is also a seamless integration because, I mean, as you can see, the user can just use these functions like any other regular native function. We also noticed good benefits on the performance and enablement side. Enablement is clear. We have seen users now calling AI inference from Presto queries, from classification to summarization, also getting embeddings. But also we noticed some interesting effect on performance. Some of these workloads, they do query processing, and then they do some post-processing in Python, probably single process on the client side. What we are doing here, we also bring in the Python execution closer to data, leveraging the parallelism from Presto. And we have been seeing here also end-to-end execution reduction from hours to minutes, actually, for some workload doing pre-training data exploration. There is a lot we didn't talk about, and there is a lot we plan to work on. I didn't talk about how we do serialization, deserialization here. Fei Long explained about JSON. These are basically JSON and strings, but we are working on a more efficient serialization mechanism based on Arrow. This will allow a more efficient encoding both for remote execution and also to minimize memory copies for local execution. These remote calls are typically synchronous, so the workers might be there, waiting for the reply. We are also working on integrating this into a more efficient async RPC framework within Velox. The functions that we are providing here are scalar functions. We are also working on extending this for aggregations in Python. And of course, we are working to open sourcing part of this, which is not in open source yet. Thank you. Thanks.
Okay, so hello everyone. I'm Zichan from Meta. Today, my colleague and I are here to talk about a gap in Velox, and we are going to discuss how to close it. So Velox has provided world-class data processing operators, which is battle-tested. So a growing number of AI workload needs these operators, plus also iteration. So we will show why this matters. We will explore the design space. We will showcase a prototype, and then we will ask for your inputs. as you can see, if we look at a set of common AI workloads, such as k-mean, for k-mean, it's essentially you broadcast the centroids, then you perform the distance calculation on each worker, then you aggregate, then you iterate. For connected components, essentially you try to shuffle the label to the neighboring nodes, then you do a mean aggregation. For multi-level graph clustering, it's similar. You do shuffle, you do mean reduce, you do broadcast, then you aggregate. So these are like data processing operators. This is essentially what Velox has built for. But there is a catch. These workloads need iteration. And Velox doesn't have iteration. So this is what we lose without iteration. So here I will show two examples. Look at the vector search. Right? To do vector search, you need to build a vector index. And to build a vector index, you need to build a code book. The code book is basically a k-mean, try to compute centroids from the vectors. Because it requires iteration, you have to leave Velox. As a result, you are stitching together two systems. You are doing data transfer unnecessarily. Similarly, if we take a look at semantic dedupe, so this workload typically involves 4 logical steps. The first step is to compute similarity pair, which you can do in SQL, for example, with vector search. And the second component is connected component computation, which you need a graph algorithm, and you need iteration. Then the third step is essentially try to do representative selection. You can, again, represent in SQL. And then lastly, you do tuning. Because for the connected components, you cannot do iteration. You have to leave the system. As a result, you have to stitch together two systems. You have to do 2 data transfer. So the cost is real. So if you want to have a single kind of query plan, then you have to figure out a workaround. You might suffer from quality loss. You also pay the cost of data export and the data re-import across system. More importantly, each of these algorithms, right, they are kind of essentially data processing, but you have to re-implement all the capability which Velox already has. And also, there's no composition between the iterative computation and a non-iterative computation. So this is not isolated. This is really a common pattern hidden in a plain sight. The common pattern is essentially you compute a step, you check for convergence, then you iterate. K-mean does it, connected components does it. Even for agentic AI, right, you do the same pattern. You retrieve, you reason, you refine, then you iterate until you have the good answer. So they can run in billions scale. So each of these algorithms, they have to duplicate the same capability Velox already has. So why Velox is the right engine? Velox is battle tested, used in many workloads, Presto, Gluten, etc. Another interesting kind of benefit is query composability. And if we kind of introduce iteration in Velox, then all the workload will get the same benefit. So here I want to show you an example what the kind of composability actually gives you. Right? Imagine first is look at vector search. Right? As I mentioned earlier, you have to do code book training, which you kind of do it in one system. Then you do the search, which is another system. If Velox supports iteration, then you can simply write 2 SQL statements. It's one single query plan. Similarly, for semantic dedupe, right, you can do everything in SQL, everything in one kind of system. You don't have to do data transfer. For agentic AI, similarly, right, today you have to do custom orchestration. If we can do iteration in Velox, then you can do everything in one system, even express in SQL. So with that, I'm going to transfer this to Jingfang, who is going to explore the design space and also showcase a prototype.
Thank you. Hello, everyone. I'm Jingfang. So thanks for Zhichen for the great introduction. So I'm going to cover about the challenges and the example of solving those challenges. So before we start, let's take a look at what the landscape looks like. So we have different systems, and every systems, they sit on one point in the spectrum. And on one end, we have the platform like PyTorch. It handles keep an iteration as a simple Python loop so that it's easy to write, but the engine can't optimize across iterations. On the other end, systems like Flink break a big iteration directly into the engine itself. It has the lowest overhead of iteration, but it's complex and highly coupled. And the question we are asking is, where should Velox land? So here we look at 3 different implementation options. So they also like sit on different points on the spectrum. So approach A, we handle the iteration by external driver loop. So every iteration we build or we rebuild the plan, the task, and the connection to use. It's simple, but we need to pay all the cost for each time. In approach B, so the difference is we use the stateful tasks, and compare with approach A, we reduce the overhead of rebuilding the plan and task each time. And approach C is the engine native iteration. So here we can consider adding a new iteration node inside the query plan, and the engine itself owns the loop entirely. It's the most powerful approach, but it may take the highest implementation or testing cost. So the right approach depends on what your performance targets and how many algorithms you want to support and how fast you want to ship it. Okay, now let's look at 2 different challenges of the design. The first challenge is the state. So Velox is built for single pass queries, which means the data flows in, get processed, and then we are done. But for iterative workloads, it's different. We need to handle the data across iterations. If you look at the data, some of the data, they are read-only, but they need to keep in memory across iterations. Other data, they change every iteration, but we still need to keep that, most likely the state data. And there's another kind of data, so they can be the output of your last round and be used as the input for the next round. And then for the convergence check across every algorithms, we compared and listed the convergence check for different ones, like k-means, connector component, and we found that they followed the same pattern. So they do an all reduce, and then for check some counters or metric, and then with that, they do a predicate. So the mechanism here is always the same. It's just the predicate changes. So for this challenge, we come up with the conclusion that we need to build 2 primitives. One is to keep the state alive across iterations. The other is a shared convergence check. So everything else will build on top of these 2. Now let's take a look at the second challenge, the exchange. Exchange means the data exchange across workers or data shuffle across workers, whatever you call it. So the core issue is also related with the Velox is designed for the single pass query. And similarly for the exchange, the exchange layer was designed for the single pass queries as well. But this assumption breaks down the moment we need to repeat this dozens of or hundreds of times. So every inefficiency that was acceptable once when you write just for a single pass became the serious bottleneck when it multiplied across workers and hundreds of times. So what's interesting is that the solution of those inefficiencies, they are not complicated. So the solutions we can consider are like we can do persistent connection, we can do direct serialized to send pass, we can do controlled flow, bounded flow control. So those solutions are all well understood techniques. The challenge is how we can integrate those cleanly into Velox architecture without breaking the existing one-pass use case. Okay, so note that these improvements are not specific for graph clustering or for vector search workloads. So any query that pushes the data with large volume across workers, they can all benefit from those solutions. And the iteration here is just to make the problem impossible to ignore. Okay, here let's look at a concrete example. Connector component is one of our core target workloads. So we use it as the example, and we build a prototype for it. So the algorithm is simple. If you haven't heard it previously, it's simple label propagation. The idea is that every vertex starts with its own ID as its label. And in every superstep or every iteration, vertices send their label to all its neighbors. And after it receives all the information from its neighbors, it do the aggregation and it keep the minimum label they receive. So when the number of label changes hit 0, then we are done. It's converged. On the right side, we demonstrate how this implementation for the algorithm is done with architecture B, or the choice B we considered previously. So it has a few, we add a few classes here. The CC plan compels one Velox plan that covers shuffle, aggregation, and apply. And outside of that, for the control of the loop, we have the BSP controller. It drives the loop. It calls the function to give the next task until converged. And like outside of that, we have the vertex state connector. It double buffers the vertex label so that state persists across supersteps. So with this prototype, we benchmarked it against our standalone graph engine. And we did the benchmark with a different scale of the graph. Like we compare small graph, medium-sized graph. And the early results give us confidence that Velox is the foundation to build on, is the right foundation to build on. So the data loading, data writing, and the apply logic are faster than our standalone graph engine. But the exchange part is still lower than the standalone graph engine. Right now, we are still working on the exchange part. Okay, the algorithm is simple, but once we go to super large scale, at the production scale, like trillions of edges, thousands of workers, or hundreds of iterations, or when we consider some complicated algorithms we need to support, the three things can break. Like memory runs out because each worker, it needs to load part of the graph. It needs to store the state, and also you need to keep the messages in the queue. And the network can also get flooded because like you may have large volume data you need to transfer, and some algorithm, they may need the same level or even larger scale level of the data compared with other algorithms. And also when the size becomes very large, we need to use thousands of workers or even more. And when we have those number of workers, some slow workers, they can host everyone else. And so we need to solve those problems when the problem comes to the production scale. And one thing we observe is that those problems, they don't show up in isolation. So they interact and amplify each other. So when we need to tackle all them together, not single one by one. So that's exactly why a general engine level iteration primitive is worth building. So we solve the hard part once, and every workload that needs the iteration, they can get the benefit for free. And next, I'm going to hand it off to my coworker, Junjie.
Yep. Hey everyone, this is Junjie. And thanks Zhichen and Jingfeng for the amazing problem space and the concrete example in this talk. I want to give a quick wrap up for today's talk and open up for the open questions we have. So where do we say that has the impact? Let me organize this by the dimensions from our trade-off matrix. So composability, one plan, one engine, instead of multiple systems stitched together through the data native language like SQL to compose execution from the user perspective. The second one is the state persistent and exchange reuse, which Jingfeng is already mentioned. It will eliminate per iteration per plan overhead. We have observed an early performance improvement by that. So engine managed checkpointing provides the higher reliability and resource reuse instead of starting from the scratch when everything fails. Of course, debuggability, one execution trace instead of several system calls, multiple iteration, debug and observability become easier. From the chart, we can tell the quickest win are the state persistent and exchange reuse. The improvement of performance and enable everything else. The biggest potential leap is the engine native iteration. It improves all dimensions at once, but this is the highest implementation cost. So we already explored the plan A and plan B, which is external driver and the state through the external driver. So those are our observations, not a roadmap. The red priority depends on which workload matter most to the community. So what does we actually gain if we close the iteration loop and gap? So no more workaround that sacrifice DevX and quality. For example, the vector search application, training, indexing, and search in one plan and one engine, Velox become the fundamental building blocks. And no data exposed. Import once and reuse the entire life cycle of the execution, which eliminates the intermediate data storage and the transportation. Hardware acceleration is by product. Like a cuDF and the community contribution bridge the gaps between Velox and the GPU, which where the majority of the AI workload happens today. And the most exciting part is the iteration support propagated to every engine built on top of Velox. So like a Glue, Presto, and so on, one code can run everywhere. So new workload, agentic workflow, clustering, and other algorithm, we haven't sort of can run Velox right now. The gap is not the compute, it's the control flow. Close the loop, and the Velox will become a fundamental building block for the iterative AI workload. But we are still in the early stage. We don't have all the answer, and that's why we are here today. And for example, what's the right level of generic? Like, do we need to have algorithm specific, or do we need to build a generic BSP support, or any arbitrary fixed pointing computation? So where should the loop live, like a driver, task, or the plan node? And how should the iteration state and interact with the memory attribution? And is long-lived and mutable, or should it be a split editable? So is the column model is the right fit for the graph state, or should the Velox support the OPAC operator state as a first-class citizen? And how do we handle the failure from the middle of the iteration? How do we reuse the checkpoint in Velox provide today? I think all those are open questions we have. So right now we have a working prototype. We tested it at the scale, but the design space is widely open. So we love to hear more perspective from the community. Yeah, thank you all.
Good morning again. Today, I'm Zichen again from Meta. Today, Akash and I are going to talk about how to make vector search first-class citizen inside a query engine. As you can see, this is joint work from many Meta colleagues. The short version I want to say is that we found that vector search is a relational workload hiding in plain sight. So today we are going to show you how this works. So why does this matter? The following scenario can happen to any AI team, right? You developed a very good embedding model, and you make vector search work. Then all of a sudden, someone says, OK, I need to filter by access control. I also need to join with user metadata. Then I also need to aggregate. As a result, you find yourself stitching multiple systems together, as the previous talk. Right? You have to kind of do the SQL, then you ship your data to the vector search, then you come back. This is a lot of hustle. So the fundamental gap is that faster vector search exists, but composable vector search at scale doesn't exist. So here is a kind of quick overview of the landscape. So existing systems actually force user into a very difficult trade-off. If you look at the vector databases, right, they are very scalable, they are distributed, but they don't support SQL. You cannot compose. There's also SQL extensions like pgvector. They support SQL, but they are single node, they are not scalable. There's also cloud solutions such as Google SQL, right? They start to introduce vector search, but they only support post filter. You have to build everything in the vector index. Again, if you want to composable kind of vector search, as I kind of illustrated earlier with the example, then you find yourself have to stitch together multiple systems, which is a hassle. So this is the slide I'm most excited to talk about. What we discovered is that vector search is actually a relational workload hiding in plain sight. If you want to kind of partition your vector space by similarity, it boils down to a scalar function, right, with a code book. And if you want to build an index for per partition, right, that's a group by, then followed by aggregation. If you want to kind of search inside a partition, right, it's an equi-join, right, with global top K. So if you want to introduce kind of new index type, right, it's opaque, right, it's just a parameter. You can support flat, IVF, or RabbitQ to your choice. So this analogy is a structural isomorphism. So we are going to kind of show how we take advantage of this. So this is the architecture slide. There are two pieces which are cleanly separated. If you look at the bottom left, right, the first thing is the code book. Right, imagine they are kind of cluster centroids when you kind of partition your vector space. So this tells you where your vector lives, and you just need to kind of broadcast your code book to all the workers. The second major building block we call local index. Essentially, this is searchable artifacts, right, you build for each partition. These are the heavy kind of part of the solution. Essentially, it can be fairly large. So the elegant part here is when we kind of partition the vector space into clusters, the cluster ID serves a dual purpose. It is both a similarity proxy. It is also a distribution key. So this makes a zero shuffle vector search possible. So on the slide, I also showed the steps. First is you assign your clusters, your vectors into different cluster. Right? Then you build a local index for each cluster. Then you leverage the cluster ID to co-locate the query and the candidate vectors. Then you perform local search. Then you do a global top K. So how much code do we actually have to write? We only need to kind of implement 3 Velox functions. First is assign top K. Given the code book, how do you assign each vectors to a cluster? The second function is build a local index. Given kind of a cluster, how do you build a searchable artifact? The third function we have to implement is search the index. Everything else, like partition, memory arbitration, etc., we get this for free. If you want to introduce a new index type, you just implement a subclass. So now let me show you something very interesting, right? Because of this observation, this decomposition, we get several capabilities for free. So the first kind of capability is zero shuffle execution. Right? In a naive system, when you need to do vector search, you have to kind of shuffle every query to all the kind of candidate partition. And if you imagine, right, if you have a very large table, and if you want to partition your table into many centroids, yeah, if you have to shuffle, that's terrible, right? But because we kind of partition both the query table and the candidate table use the cluster ID, right? The query becomes local. And imagine you kind of partition your cluster into 10K centroids with an mprop of 10 and 100 worker, right? Each query only need to hit 10 shards. As a result, you only search 0.1% of the corpus. And the network saving, right? If you have to shuffle everything, you have to kind of shuffle about 1.4 terabytes if you have 1 billion vectors. But today, we only need to broadcast the codebook, which is about 200 megabytes. You got 7,000x reduction in network traffic. The second consequence is a memory-bounded index. Right? If you have a large table, let's say you have 1 billion row, each with 1,000 dimension, with 32-bit for each dimension, you have 1.37 terabytes. And we employed 2 techniques. One is a new index type called RabbitQ. With RabbitQ, it gives us an over 99% recall with about 4x reduction in terms of the index size. The second technique we employ is called subclustering. So in real world, right, when you partition your table into multiple clusters, they are highly skewed. So in one of the workload, we saw that the largest cluster can be 7 million row, which is 100x the average. So the technique we employed is called a subcluster. Essentially, we break large clusters into a subcluster and cap it. As a result, we see 25x reduction in terms of index size. So the next consequence is guaranteed result under any filter. As I mentioned earlier in the example, because build index is a standard SQL aggregate, right? You can do a where clause to first filter down your data, then you build an index. As a result, you basically don't lose any recall because this is a SQL decomposition. So lastly, I want to show the power of full SQL composability. Right? For many workloads, you can express most of them in a single SQL. For example, you use where clause to do the pre-filter. You build an index on the filtered data. Then you search for top K. Then you can join with the metadata. Then you can also do a group by to do aggregate. If this is with external database, right, you have to kind of ship data to the external database, then ship it back. That's a lot of hassle. You also have to deal with consistency issues. So next is about a design issue we have to wrestle with. Right? For expert users, they want to complete control of the kind of topology. They also want to control the mprop and many parameters. But for novice user, right, they just want something they can use. So to solve this problem, we essentially support two levels of API. The first level is we call the primitive, which are the three functions I mentioned earlier. Right? The power user can do anything they want at the cost of very verbose SQL. For the novice user, we introduce a syntactic sugar we call level 2 API. Right? So you can write a very concise declarative SQL. And we leverage the optimizer to convert from level 2 to level 1. And with that, I'm going to hand this over to my colleague Akash, who is going to talk about evaluation. And,
Thanks, Jishan. Yep. And thanks for covering the architecture and then the consequences as well. Yep. I think we'll go over the evaluation next. So starting from the proof, we actually tested the scalability on two different benchmarks. One was 700 million corpus and another one was 1 billion candidate row. So I think in both of these, we see that the scalability is actually non-linear. Like in the first one, when we move from 70 million to 700 million, which is a 10x increase, the time actually increased by, I think, around 3.1x only. So that's a sublinear increase in time taken. The second one, which is the deep 1B use case, where I think we have build plus search, which is completing under 2 minutes, and the recall is around 96%. The rabbit queue, which Jichin talked about, that achieves the same wall clock time, but at a 25x lesser memory. So, which basically shows that the compression is coming effectively for free here. Yep. Moving to 4 real workloads and 3 different modalities. I think the first one, which we are the most proud about, is the entity matching at 2 million queries against a 2 billion candidate. This used to time out earlier, even when we sampled it down to 0.5%, but now it completes within an hour. The W2 through W4 shows a 3 to 10x speed up at 95 to 99% recall. So moving to a practical question which comes on whether we want to have pre-built indexes or build indexes on the fly. So pre-built indexes are generally faster if you have repeatable queries. So it's like 1.7 to 2x faster. But for on-the-fly data exploration, it's actually better to build the indexes on the fly. So our recommendation is use pre-built indexes if you have a repeatable query, and use on-the-fly indexes for exploration. One of the other surprising finding was when we were doing profiling, we found that 99% of the CPU cycles actually go to cluster assignment routing. Index building and search, it takes less than 1% combined. So that was not something which we had expected. It validates that HNSW routing is a critical optimization lever, and we'll talk about it in the future work also. I think using GPU accelerated routing can improve some of these bottlenecks. So tying it all together, we saw that we have 7,000x less network overhead from codec partitioning. We also are using 25x less memory, given we are using RabbitQ and subclustering. We have full SQL composability. And we have 2 ways of building vector search. It's either the power user experience, which is 68 lines of SQL, or the novice experience, which is 12 or 2 levels of API, basically. Yep. So yeah, I think the key point is that these emerge from one decomposition, and they are not separately engineered features, basically. Three lessons I think we took away. The first one is that building bottoms up. So prove the primitives work, basically at billion scale, before committing to the syntactic sugar. The second one, which we think about the most, is that the hardest part was realizing that we didn't need a new engine. We spent weeks designing new plan node before realizing that existing UDFs were sufficient for this use case. And the third one is code quality matters a lot more than index algorithm. So tuning your centroid is the best thing we can do, and the rest will follow. To close, we showed that vector search is a relational algebra. We have zero shuffle execution. We have memory bounded indexing and a two-level API. We have 95 to 99% of recall, 3 to 10x speed up, and 7,000 times less network. The future work will revolve around GPU routing, streaming updates, adaptive index, and multimodal capabilities. And then the deeper lesson I leave here is that we didn't build vector search as a new engine. We discovered that SQL engine already had one, and we kind of built the support inside of it. Yep. And with that, yep, thank you so much.
Okay, we are at lunch, which is great. Lunch will be served the same place breakfast was. Feel free to take it outside. I think the doors are unlocked to come in. We also have the room called Chips and Salsa across the way, which is open for us to use as well. So I think we'll be back in about an hour or so. test. All right, folks, we're going to get started. Hope everybody had a lovely lunch. In an effort to keep us on time, I'm going to introduce Meng, who will be giving a keynote this afternoon on the Velox I/O layer. Thank you, Meng.
Hello, everyone. So I'm Meng from the Metas. I'm a software engineer on the Velox and Presto team, and we focus on the recommendation system support. And today I'll cover the recent advancement we made into the Velox I/O layer. So including the Nimble file format extension for the training data normalization solution at Meta, and also the recent open file format support for the Meta internal open data lakes efforts. So here is the agenda of the talk. First, we will give an overview of the Nimbles and how its current state in Meta. And then we talk about the extensions we made to the Nimble to support the training data normalization and Metas. And then we talk about the user sequence normalization and how Nimble help to improve the serving efficiency. And next, we talk about some of the new index types we're building into the Nimble file format. And then we talk about the I/O optimizations for the interactive workloads optimization. And last, we talk about the open file format efforts and our vision for Velox-based open data lake foundations and the current working progress. So Nimble is the high-performance column file format built at Metas. So initially built an ML workload, and currently we are kind of cover the interactive workload as well. So today, 80% of the training data and roughly 40% of the entire warehouse data is stored on Nimbles. And we roughly see like 10% of the storage footprint reduction and 10% of CPU efficiency on serving side, on training side. So Nimble is the fully open source, and compared with other open source file format, we have what's the difference? We actually three differences. First, Nimble support custom encoding, so we allow the recursive nested encoding. So for Parquet, for each column, we can only pick out one encoding type. But for Nimble, for example, if you choose wrong length encoding, for a column, it will produce two substreams. One is value streams, the other is the wrong length streams. For the value stream, you can first apply the delta encoding, and on top of that, you can recursively apply the var int encoding. For wrong length encoding, you can choose the bitpath encoding. So each substream can choose its own encoding to optimize the data patterns to maximize encoding efficiency. The second is the encoding selections. So during the write, Nimble collect data statistics like the min, max, and the unique count. And then for the list of the candidate encodings, using the estimated encoding size and weighted decoding speed, and to calculate a score to pick up the lowest the encoding with the lowest cost. And the third is that we are building the cluster index into the Nimble file format to support the key-based data skipping. And Nimble file format itself is extensible, so you can add a new index and encoding without modifying the core file format. So next we'll talk about the recent extension to the Nimble file format to support the training data normalization. The first Nimble serializer. So Nimble serializer is the serialization protocol. It converts a Velox vector into a Nimble encoding byte stream. And it's the wire format for network transportation and serving. And it has three main components. One is the serializer, which is convert the Velox vector into the serialized bytes, and then the deserializer, which is do the reverse. And then the projector we recently added to do the feature projection without decoding. So, and we also implement three key features to enable this. So first, we added the flat map encoding into Nimble serializer. So with flat map encoding, each feature is independent stream. So do the feature projection, we basically just selected the byte streams without decoding. And the second, we integrate the Nimble serializer with the Nimble encoding framework. So this allows per feature encoding selection and customization. And third, we added the coroutine-based parallel decode optimizations, which can significantly reduce the wait time and the client side and with minimal CPU overhead. So next one, we'll talk about the cluster index. Cluster index is a value index. it provides a key-based stripe pruning and row range stripe and row range provings. It requires data to be sorted and using 3 levels of binary search. At the first level is search, at partition level is search partition key to find what the key locate in which partition. And then once we locate the partition, we do second level binary search to find which chunk in the partition have the key. And then at the row levels, we decode the key stream and using the string comparison to locate exact rows. So we also provided the key encoder. So key encoder can encode a composite key index column value into a byte stream which is string comparable. So other than the training data normalization, class index can also help the 2 use case query access patterns. So first, just for the regular scan, we automatically to convert the filter on the index column into either the pointer lookup or the range scan. For example, if the query has a val clause, say the user ID equal to 123 and the timestamp is greater than a certain data range, we will convert it to the index bounds with the upper bound and lower bound. And then during the scan, we can just filter pruning the stripe and the row range and only to decode and load and decode the matched row ranges. So cluster index can also help the index join to do the batch index lookup against the warehouse table with Nimble cluster index. So we store on the remote storage. And currently we have finished end-to-end integration with Presto for that. So next one is the chunk index. So chunk index, the position index, is provided from the row to chunk mappings. So it requires no data sorting. It decoupled from the cluster index. It can help in the 2 workloads. First, it can be used with cluster index. So cluster index is the map from the key to the rows, and the chunk index map the row to the chunk so that we can directly jump to the chunk without sequential decoding. It can also help the filter push down. So we can skip decoding the chunk which doesn't match the filters. So then we talk about how the Nimble file format can help the training data normalization. Before that, we first talk why we do the training data normalizations. So in matters of modern AI training, kind of using the larger user sequence and the longer sequence and the long retentions. So these all cause exponential growth of the training data storage. And the problem is that the training data is denormalized. So the same user sequence got replicated across multiple training samples. The solution is the training data normalization. So basically, we extract the duplicate user sequence into the extendable, indexable storage system like REST, DB, and ZB. And then when DBP, the Meta's internal training framework, do the trainings, they will join the user sequence from ZB through the user ID and the time range from the training sample, and then merge with other remaining features to reconstruct a complete training samples for trainings. And we also, for the warehouse interoperability, we also replicate the normalized training data in warehouse and provide queryable through the Velox join algorithm, like index join, hashi join, and submerge join. It depends on what kind of workloads. So now we talk about how the Nimbles help the training data normalization to improve its efficiency. We currently partner with the ZB and the RexDB team to do the rollout in the 2 stages. In the first stage, we call it the hybrid Nimble SD file hybrid Nimble format. In this format, the data is still using the SD file format, but the value is using Nimble thread to decode. With the Nimble threader, we allow the ZB to do the fine-grained feature projection server side. So the projector we built can do the feature projection on the serialized value we read from the SD file. And then the benchmark results shows that we can reduce the projected bytes we sending from the ZB server to the client. And the client side, we optimize the decoding. So we see the signal reduction on the CPU time and word time. The benefit of this stage, we don't need any kind of infrastructure change to the DB server. And it can help to quickly to unify the fragmented custom encoding into one format, Nimble encoding format. The second stage after this is the kind of end state to replace the entire SD file with the Nimble custom index file. So then we will have one file format for both training and the analytical queries. The columnar file formats can give us additional benefits on I/O efficiency through the fine-grained per feature I/O projection. To minimize the server-side CPU cost, we were using Nimble Threader to pack the projected feature streams at a stripe level and keep the encoding all the way from the disk to the client side. So to minimize the overfetched rows, we're using the user-aware striping. So because each query is only for a single user, so user-aware striping ensures that for each stripe, it only contains the user sequence for particular users. And then the cluster index can exactly locate the exact row range. So the client side will only decode and match the rows. And the preliminary results shows that for the user sequence with range scan, the column index solution can be performed much better than the ST file format. Next, talk about some new index we are currently building into the Nimble file format. So we have built a dense index. So this index is using the hash table to look up the key. So when the key comes in, first calculate hash for the key, and then based on the hash, we locate the bucket, and within the bucket, we do the key comparison. So this index doesn't require data sorting. When using Nimble in some of the, staging layer, which need a faster file injection, so we don't have to pay the data sorting cost like SD file form or Nimble cluster index file. And also, we provide optional per file Boolean filters to quickly check whether the key is in the file or not, so that if it's not exist, the entire lookup can be skipped. The hash table index itself can be partitioned and load on demand. So since we don't require the data to be sorted, so each file can have multiple such index with one per each different column index. So the other index we are exploring is vector search index. We follow the similar approach like Lens to embedding the vector index into the Nimble file directly. By co-locating the file and the index, we can always ensure they are consistent, and also one index for file format can be used by different query systems. Next, I'll talk about some of the optimizations we plan for to improve the interrupt warehouse workloads with the Nimble, like the selector reading and index-based data skipping and the encoding tuning. We plan to improve in the following three areas. First, we plan to modernize our I/O stacks. We are moving toward the co-reading-based async I/O for the lightweight CPU scheduling and the high concurrent workload. And we will continue investing in I/O coalescing, like merge small read into larger one, but still kind of try to avoid the excessively old reads and the highly selected interactive workloads. And the third is we integrating with the Sally cache for the local and remote flash acceleration. So Sally is the Meta's internal cache solutions. The second area is the encoding improvements. The first, we are seeking for the better encoding selection. One is to allow users to specify the custom cost function based on data patterns. The other is the ML assisted offline encoding selections for training data. So the other is the encoding exploration. There is a use case that they try to normalize the dense features. For that kind of use case, we have to use column format. But the query pattern is the point to look up, which means that we need to support very efficient signal encoding to fetch the single values without decoding entire block. And the value could be a scalar value or the nested value. The other will continue looking into the whiteboard encoding. Like for current string types, we only support the generic string comparison. So we are looking for explore some encoding like FST, so that find a good balance between the encoding efficiency and the decoding speed. The last is the file format extension. We are currently adding the dictionary sharing and the dictionary encoding preservation cross chunk and streams for better to reduce the storage, I/O, and the memory cost. We also try to exploit the cross-stream similarity to avoid the data duplication cross-stream for some training data use case. And we are currently adding the fine-grained stats to enable the filter pushdown at both the stripe and the chunk level. The last, we'll talk about the recent open table format support. So the industry currently have converged on the modern open file format like Iceberg and Pymon. So Iceberg is the leading standard for the batch analytical, and the Pymon is kind of emerging standard for the streaming read and the near real-time batching. So compared with the legacy Hive table format, those modern open table format has the following key capabilities. So one is manifest-based metadata, which include the partition spec stat and the per file tracking and the file stats, which allow quickly we can allow the query system to do the query optimizer to do the multi-level partition, like partition level and the file level prunings without slow folder listing and footer parsing. The second is the manifest file-based immutable snapshot mechanism. The architecture-wise, is easy to support ACID transaction and time travel and incremental query processing. The third is the filter ID based schema resolution is safer than the Hive. In Hive, it maps the columns based on the ordinary position in the schema. So whenever you use a drop columns or reorder columns, it will breaks. But in the Python and Iceberg, they assign unique field ID to the columns and never used, so it's safe to do drop column or reorder columns. And third is partition evolution without table rewrite. In Iceberg, the partition value is dynamic calculated based on the partition spec and the column values. So whenever there is a partition change, the metadata record the old files partition spec and new files partition spec, and the query about know that will generate the remaining filters for the old partitions. Even though they're not very efficient, but it's better than the Hive. In the Hive, have to rewrite entire tables because Hive partition is fixed value, is part of the schema columns. So due to those reasons, so Meta internally have a couple efforts try to adopting those open table formats, including both Iceberg and Python. So why does this matter for Velox? And Velox is the shared execution layer. So we have one connector implementation will benefit all the query system built on top of the Velox like Presto, Sprout, and DPP. And then it eliminates the per engine integration cost. So our mission is kind of to build the foundation layer for the open lake solution, both inside Meta and outside Meta for the open source community. So the foundation spans three layers. On the top is the Axiom, which is query planning. So Axiom will understand the open file format metadata, will do the partition and the file levels filtering, and also do the speed generation to create working unit for execution nodes to execute, and also associate the deletion and do the deletion file and deletion vector associations. So the end goal for the Axiom is to unify the open table partition integration. So once we implement on the Axiom, all the query system built on top of Axiom will directly benefit from that. So Velox is provide a vectorized query execution and the connector abstraction interface. So different query system on Velox can get a consistent read-write behavior through the connector. And this layer requires is performance critical. For example, for the merge read, it requires efficient to load the deletion vector into memory and then filter out the deletion rows efficiently. And all these are kind of optimizations and functionality can share across different open table formats through the connector utilities. So for example, both Python and Parquet has the deletion vector support. Meta internal MetaLake also has deletion vector support, so they can all share the same optimizations. The last layer is the bottom layer is the storage layer. So we use a Nimble to do the physical data storage, and we can leverage Nimble's extensive encoding and index capability to optimize the physical I/O performance of open table file formats. And the Nimble is fully open source, so our goal is to position Nimble as one of the supported open file format for those open table format, like other than the Parquet and ORC and the Lens. Yeah, so last is a quick update of the current connectors stats. So for Iceberg, we have feature complete and to the V3 versions. And on read side, we support predict pushdown, column pruning, and feature ID-based schema evolution and deletion vector handling. On the right side, we support writing data file writing and deletion vector generation libraries. And we next step, we will kind of tune this kind of performance in Meta use case, and also adding the support for Nimble file format, like the adding the field ID schema management inside the Nimble file format. And we're also working with other Meta internal infrastructure team to adapt to the Meta infrastructure for store integration and replication. For Python side, we currently actively adding the basic read-write support for append-only table for the initial near real-time use case at Meta. We also welcome the community to adding the primary key-based support if you see how the use case. The other thing to mention that the DB team in Meta is building the streaming lake solution called Flux. And so basically the more recent data is the new data is written through the SE file, and then the old historical data, they compact into the Nimble columnar format with the class index. They built the Flux reader connector in Velox and provide transparent access to both type of file in Presto query and Spark queries. Yes, that's all I have. Yeah, thank you.
Yeah, he can. Okay. Next, we have Elodie from Meta talking about Velox on DPP.
Hi everyone, my name is Elodie Lee. I'm a software engineer in Meta. So today I'm going to talk about how we leveraged Velox to accelerate Meta's machine learning AI data loading for recommendation systems. So this is the agenda today. I will first give some context for DPP and the previous in-house compute engine. I know both Marsha and Pedro has talked about this, but just as a quick recap, I will just quickly go through it. And the second point is that I will talk about why we want to start to leverage Velox. And then I will talk about the migration journey and where we are, like where we start from and where we are today. And the fourth agenda is that there are some challenges, pretty interesting challenges we encountered that is also unique as compared to a practice-MO migration. And next, I will talk about like what we're doing right now on top of Velox, and then what are the future opportunities that the open source community can help us. So first, what is DPP? So DPP is a specialized compute engine built for Meta's recommendation system data loading. So the entire engine is designed to keep the GPU busy, since GPU are the most expensive resource. So the engine basically does pretty heavy data transformation, prepare the data on GPUs, and then send it. Then the data will be pulled from GPUs, the client in GPUs. The engine supports checkpointing, so the jobs can be preempted and resumed later. The engine's data consistency contract is at most once. So it means the data loss is like okay, but data duplication is bad. So this diagram, I borrowed that from Marsha's talk last year in VeloxCon 2025. Basically, this compute engine is a two-stage pipeline. So the heavy data transformation happens on GPUs, and then there's arbitrary data exchange between GPU and CPUs. zoom into a single CPU host, what happened there? This host is what we call a DPP worker. The data transformation follows a pipeline-like structure with 3 major steps. First, the query processing, and then the engine IR produced by the first step is then fed into the second step, which does the tensor encoding. And then the tensor data will be fed into the next step to do the tensor-based transformation, mostly on PyTorch. This query processing part, before we leverage Velox, is using an in-house engine called Koski. And it does map-only processing. So what is Koski? Koski is library, a compute engine C++ library that offers 3 layers. The language layer, which runs on launcher for customers to generate query using data frame like APIs to describe the training intent. And then on the DPP control plane, it runs query optimization and switch generation to prepare this query to be run in distributed environment. And then the plan is dispatched to DPP worker, where it executes like the split by split. So the DPP worker execution is the part we are replacing with Velox. There are some details that the Velox will be running on DPP control plane as well. Next is like why we're doing this. Like we have an in-house engine already. The reason is that the AI training is fast moving. So there are a lot of quick experiments and ever-changing requirements we got from everywhere. And training paradigms also shifting. For example, the industry trend is that recommendation system train on longer and longer user sequence to deliver better personalization. This requires the data normalization to scale, meaning the data, there are more paradigms we need to support on data joining, merge join, index join, broadcast join, and also we to support more complicated data processing pattern, we need to use building blocks like nNest, streaming aggregates, etc. And this is not available in the in-house engine. So without this flexible, without a flexible yet reliable infrastructure, to meet the ever-changing requirement, there are a lot of customized workarounds to fill the gap. But each workaround built on top of another workaround sometimes start to break another workaround. So eventually the velocity slowed to a crawl. So this graph kind of describes the cycle. So it starts with the engine lacking building blocks, and then the team start to build like workarounds using at the disguise of UDFs. These UDFs are actually not the traditional UDFs. They are like mini engines or mini services running in disguise of a UDF interface. And then the team spent more time to build customized workaround and maintaining that. The time should be instead be used to build the building blocks. Then we are back to the beginning that the engine lacks building blocks when the next request come. We are to break the cycle. We started the VeloxCon project. As the name suggests, it's a hybrid of Koski and Velox. So when I first started to work on this project, I look into like what does Velox mean. Apparently it means fast and swift in Latin. So apparently this name means faster Koski, I guess. Yeah, Velox solves the hard problem already. It is battle-tested in Prestissimo, Gluten, and Extreme already. And then also it's a library, so it's composable and pluggable to DPP engine. So how does VeloxKey work? So we still use COSKey to handle the query authoring and optimization and split generation, and Velox takes over the execution. Even for the execution, we are doing some phased development changes. So we have 3 adapter layers. We adapt the connector. So right now we're still using the in-house connector. We're going to use Velox connector next. This one. We're going to use Velox connector. And then for the UDFs, which I will touch later, we'll also have an adapter for the UDFs. We're not rewriting UDFs in this stage. The next is the output IR. It is still in the form of COSKey IR that is backed by Velox vector. In this way, the downstream usage customers doesn't need to change their usage of APIs. So what is the migration strategy? Our goal is to achieve infra-transparent migration. Sounds obvious, right? But there are some nuances that this is not an easy goal to achieve. But I will talk about the strategy first. So in the very beginning, we started, this adapter approach was kind of designed pretty early on. And then the IR adapters and connector adapters were built. And then the second phase, which is in the kind of late, in 2024, we started to tackle the UDF migration. So we introduced the UDF translator to allow COSKey UDF to be registered in Velox registry, and also a UDF adapter that lets Velox execute COSKey UDF during batch execution time. So then the next step is that we need to build a strategy for large-scale migration once we validate, okay, most of the queries should be able to be executable in Velox engine. So we spent time learning from Pratisimo's experience. And we don't want to solve the problem that Pratisimo already solved. One key lesson we learned is that a large migration has to be verifiable against a baseline. So we built a validation infrastructure that doesn't just work for VeloxKey, but work for general DPP engine. In phase 3, we focus on the general stability clean house by doing a large consistent sampling for production jobs every day. And then we basically categorize all the errors and then conduct fixes and eventually reduce the stability crash rate from 4% to 0.63%. And then phase 4 is we're ready to do actual productionization. We start with this model-based rollout. For the model, you can think of it as query groups where their query shape falls under a spectrum with some similarities. A few highlights here are like on correctness, we built a deterministic text-only rewrite framework so that we can verify the query even though they are non-deterministic. On performance, some highlights are we worked with Velox team and introduced a task barrier support for reusing execution plans. This is because DPP engine needs checkpointing. And phase 5 is where we're at. We're undergoing a long tail rollout right now. We're rolling out models, query groups, batch by batch. So this is the migration timeline. It started not fast because we start to build this kind of foundational pieces, and then in late 2024, in February 2025, we start to build a validation and rollout bar, and then after talk to Pratisimo folks, we basically decided to build a testing infrastructure, in around July last year, the infrastructure is mature enough to support initial rollout. And then we finished the most complicated model rollout in October last year, half a year ago. And then after these hard phases in January, we're already at 20% of VeloxKey migration in terms of compute power. And then as of today, we're actually at 92%. It's increasing every day. So by the time I prepared this slide, this number was like 80 something. Now it's 92 something. And also, as of today, we already locked down the query shapes that allows to run in the previous compute engine, and all the new ones will be default running on VeloxCon. And we are right now targeting end of September to finish 100% migration. This chart gives an overview of the migration timeline that after we finish the validation, we resolved a lot of the bottlenecks in performance and have a framework to validate indeterministic queries. This rollout is actually exponential. The progress is exponential. So talk about challenges. What are the challenges we faced? So we encountered many challenges, and many of the challenges I listed here is a bit unique as compared to Practissimo. So first of all, in Meta's training, there is no systematic exact data match correctness baseline. Roughly correct, as long as the model do not regress, was the bar. As the models can often tolerate some noises due to data corruption. This certain noises also has blurry threshold. So because of above, there was no systematic validation infra to test and validate the stability, correctness, and performance. Even in the DPP engine, we don't have such testing infra. So changes usually needs to go through a very lengthy validation that involves the whole training workflow. This validation cycle often requires a lot of GPUs to be there to conduct the validation. So this is we need something better to empower a fast migration. So the next challenge is the quote-unquote UDFs, which I will talk about later. Also, the next challenges are the UDFs and the downstream consumers, also owned by customer code, are directly accessing the engine AR before it becomes a stable format. And these customer codes also have bugs that engine cannot adapt to. So we had to go and fix customer code to make this happen. Finally, we also discovered performance bottlenecks, especially on query plans with large amount of expression nodes. I will talk about each one and how we solved them. So first, on the correctness baseline and determinism. So the hardest part of this migration of establishing the correctness baseline was not swapping the engine, but just defining what is the bar. And during the process of migration, we identified 10 plus correctness bugs in user code. And a roll-off of each bug is painful since we had to assume that the model that's being trained has adapted to the bug. So, for example, it took 5+ months for us to roll out a single null bug fix that has a larger blast radius. The rollout is still ongoing to finish the fix of this bug. So more on the building the testing infrastructure. So to address the problem to establish a correctness baseline, we build a testing infrastructure. So by building this, we have 3 principles. First, we have a debugging first mindset, meaning like whatever we validate, we have to be able to debug and root cause it quickly. Second is the scalability. So we leverage the map-only schematic of this data processing, and then we also does checksum-based validation, so you can run fast and validate many queries, actually 100% queries every day for the rollout models. And third, this infrastructure must be generalized to not only work for this migration project, but generalized enough to validate all DPP engines correctness. Yeah, so I will skip some of this because I think I have a lot more to talk about. But for correctness, one thing that is interesting is for debugging, the data frame API is harder to rewrite. So instead, we implemented a bisecting tool. So we basically do binary search on the nodes and to find which node brings, what is the lowest leaf that brings the mismatches, and then that speed up the root cause of correctness issues by a large margin. On UDFs, the UDFs in DPP is very unique. Practitioners UDFs are usually more content, but for DPP, the UDFs are like black box UDF. There are a lot of black box UDFs by themselves. So these UDFs can run, for example, a mini Presto inside. And some UDFs, they run other engines that execute hundreds of stage computations. Some UDFs access arbitrary data source outside of data warehouse. And some UDFs, they cache some data and do this hash join equivalent. And there are also a lot of the the Koski also have a uniqueness in the Koski UDF, that Koski has a special UDF flavor that doesn't have a static signature. So the signature is resolved runtime based on the input. So how do we solve this problem? First, for the UDF, we basically chose to write adapter to adapt UDF instead of rewriting all of the UDF, because it's not really possible. So for the adapter, we have two parts. One is a UDF translator that handles type binding and function registration. This prepares the execution plan, as Velox knows how to call these UDFs. One interesting detail here is that, as I mentioned about the dynamic signature. So basically, for the function translator, there is a initial version. We have this dynamic registration to dynamic wrap the UDF based on the signature, and then register it as a static function signature in Velox UDF registry. And at execution time, there is a UDF adapter to adapt the different engines IRs back and forth, so that the execution can run Koski UDF's code unmodified. And later, we actually upgraded this translator side to use a special form extension to handle dynamic signature. Because of these very interesting UDFs, you can imagine there's a lot of problems, and especially on its non-deterministic. So we discovered many, so basically the non-deterministic rate for the training query is very high. It's more than 90% of the query, or sometimes close to 100% of the query is non-deterministic. So some common source of non-determinism, including the UDFs that uses random generator, sometimes very deep in the stack, due to the kind of the UDF that runs mini engine inside. We have to hunt down all these random generator usages. And there are also kind of a UDF that access external data source without snapshot guarantees, and UDF that use third-party library that does computation like eigen library that can bring undeterminism. And then there are also UDFs that uses the library that gives different results based on the hardware type. And also there's a UDF box that just cause undeterministic results. For example, some C++ initialization box. Okay. The next challenge is the problem with direct accessing the data IR before the IR becomes stable. So back to this picture. So the red part marks the user code interface area. So the UDFs can have it. And the tensor encoder also just take the IR directly and change and do the tensor encoding. So The problem with this is even though maybe some query we have a match after the DAG, after the query processing, the tensor encoder can have a mismatch because of there's some bugs. One example of the bug is that for Koski IR, the contract is flat, and also the range are continuous. So this has problem when, for example, there is a array type that you can, the downstream consumer can ignore the sizes, but only use offsize to access the data. Quickly on performance. So for performance, we discovered some very Velox-related performance problem, especially on the queries that has deep expression trees, and also when we are running queries against a streaming service, which means the batches are much smaller. So the bottlenecks can be in the type binding, can be during initialization, and it can be can be within the UDF adapter, and it can also come from the batch processing in UDF, for example, the peeling and handling of encoding. Smaller batches exacerbate this problem even further. So this screenshot, I also borrowed from Marsha, showing how big a plan can be for a training query. So last week, we saw a training query that actually contains like 4 million expression nodes. So how we are solving this and how we solve this. So for the for the UDF adapter, we actually are optimizing on the adaptation layer to reduce the initialization cost, for example. And also for some UDFs, we're starting to rewrite them to Velox native. For initialization cost, we basically with task barrier support, we are reusing the execution DAGs across threads. And for type binding, we introduced a function cache to bypass the signature complexity lookup for return types. And for the overhead of batch processing, these works are still ongoing to optimize on these kind of query shapes. So what's next? We are building a lot of features on top of VeloxKey. So some notable things are we are actually working on integrating with Velox connector that we can further push down data filter to the connector layer. We're also kind of start to tackle these black box UDFs. For example, for mini engine UDFs, we're going to unboxing it and express it using compute engine building blocks. And yeah, so these are the list of things we're doing right now. And then something like more maybe future thinking are we will explore Axiom integration, and also some more optimization and query processing. For example, we want to vertical partition the query plan and then execute it in different threads, and then maybe stitch it back together later. Yeah, that's all.
Okay. Hey guys, I'm Hitarth and my colleague Jay. We are here to talk about Uber's Presto journey from 0 to 90% in Velox. So Velox migration at Uber scale. So we did this with approximately 4 engineers. We migrated 500K plus vCores. And we are reading 100 petabytes per month, approximately serving 10 million plus queries per month in Velox clusters. We have been coming to VeloxCon for last 3 years. 2024, we had 0 Velox presence. 2025, we were supporting approximately 10,000 different query shapes, running 3 Prestissimo clusters. We migrated around, which accounted for like 20% of our Presto in cloud. Current status, we are at 90% of data read. As you can see, the blue bar, which is approximately 90% of 100 petabytes. And approximately 25 clusters have already migrated to Prestissimo. This kind of accounts for 10 million plus monthly queries. So how we started carefully. We started with something what we call a shadow mode. We were basically running all our queries in our Java clusters. So whatever was running in production, we would take certain queries, run it in our Java clusters, and rather run it in our Velox staging clusters. And if they were passing, we would put it in our eligible fingerprint list, which is like a query shape. And those were the eligible queries which can run in Velox. So we started with that approach. And what we found with that approach was, why we started with that approach was basically we wanted to only run verified queries so that we know that this query shapes are working correctly. They do not have problems of it crashing on the clusters, causing other queries to fail. And yeah, so, but running all these queries on a staging cluster is painful, right? Like you basically running queries twice. It becomes a bottleneck, and after some point of time, we thought that this is not a scalable solution if we want to reach, 100%. So I think that's when we started with the second phase where we flipped eligible fingerprints with ineligible fingerprints. So we now were making all queries go to our Presto Velox clusters. Whatever was crashing, we were putting it in our ineligible fingerprint list, and we were retrying that on Presto Java clusters. So in order to even get started, we had to do a lot of Parquet enhancements. Uber is having all of its data, if not, well, most of its data in Parquet, and there were a lot of issues initially. So I think one thing that helped us a lot was the backward compatibility testing, where we took the Parquet Java unit test, rather Presto Java unit test for Parquet, and made them run, same test, made them run using native Parquet reader. So that actually helped us uncover a lot of issues, and we were able to kind of fix a lot of them, especially related to backward compatibility of Parquet versions. On top of that, we also have something called as CLAC, which is column level access control, which we have at Uber. It's an open source feature in Parquet, but it was not there in Velox Parquet reader. So that is something that we implemented. There were also issues on row group skipping. We also had bunch of our Parquet files which were having humongous Parquet footers. So those queries would kind of take up a lot of memory, cause crashes. So we were able to kind of identify which tables were having such large Parquet footers and were able to eliminate those. Result correctness was a paramount. So as we started cautiously, right? We were using verifier extensively to identify which query shapes we are supporting and which query shapes were causing any result incorrectness issue. We uncovered a lot of issues. I've highlighted 3 issues here. First one is the complex type where a null handling issue was causing incorrect results in Parquet Reader. The second one, when we were migrating our XP workload, which is heavily using CTAS queries, and at scale, Parquet Writer was having some incorrect issues, which we were able to fix as well. Then there was also an issue with wrong result due to column skipping, which was again in like Parquet Reader. All this we have already kind of committed to open source as well. I'll hand it over to Jay to talk further.
Yeah, so I'm going to talk about a few key learnings that we had through this migration. So first of all, like Hitat said, we were a team of 3 to 4 engineers. We had to be very focused during the migration. Of course, everyone wants to work on complex things like improving efficiency or memory or doing something in joins, but we had to be very focused. So our strategy was simple. We used to adopt everything from open source, and whatever has issues or bugs, missing features, we used to implement it. So the goal was clear in our heads. We had to just migrate as much traffic as we can, as quickly as we can. So for that, we had to be metric driven. So we had clear metrics on what we need to do and how do we need to do. So for that, we had like a unified dashboard, which I just have a screenshot. That dashboard has metrics like system, CPU, memory, file descriptors, also precision metrics, right? Like from open source, basically memory arbitrator, allocator. So one key thing that we learned was that most of the metrics in Presto were already there in open source. We just had to make sure we understood what they represent and add our own where we needed. So that was our focus, having metrics, using metrics to see what was wrong and fixing them quickly. Yeah, so one of an example of using metrics was when we just found an issue where there were a lot of fragmentation in our workers causing ooms, and the memory was not, the RSS was not stable. So the below graph just shows the RSS before and after. So using the dashboard, ruling out things, for example, first we ruled out maybe memory leaks in different places using metrics, and then we finally made some theories, did some testing, and finally, when we just switched the default allocator to Gmalloc, we found out that everything was gone and the RSS was stable. So just an example of the previous slide. Yeah, another key learning was to audit all the configs. So most of the time, when you're working with open source, you just accept the default configs. But for fast-moving projects like Velox, for example, it's really important to know what you're pulling. So in this case, just an example that one of the config was lesser than the other one, which led to some queries with some cryptic errors, like failed to, something like that. So it's same, using metrics, we figured out where, like what was the anonymity, looked at the code, and then we figured it out. But yeah, that was a key learning for us. Yeah, another, just to point out, not like learning, but we found out that the async data cache of Velox was really useful for our use case. So as you can see, for our experimentation, it hits around 80 to 90%. Sure, the workload is questionable if it's hitting that high, but still, as you can see, it's still useful. Even for our interactive workloads, it's around 40 to 45%. So I think it's really important for us. Next slide. Yeah. So a few investments we have done, which are in the storage layer. So Uber is migrating to cloud on GCP mostly. So one of the optimizations that we worked on was using the gRPC C++ client. So open source Velox currently uses an HTTP-based client, but when you work on GCP and accessing GCS, you can directly use gRPC-based clients, and as you can see on the green path, you avoid a network hop. So using that, GCP could give us more bandwidth in our own zone. So that was one thing we worked on. Also, we are working with the GCP team closely on like bidirectional read, using the same connection, and maybe even reducing operation costs as well as latency. Latency for maybe AI workloads, if we do invest in that. Also, we are also experimenting with some Alexio as a remote cache. So as you know, in cloud, operation costs are everything. And we're trying to see if we can, better improve our cache and have a better, like a lower bill on operation costs. Yeah, so finally, so before the migration, everyone knew Velox was good. There were TPC-DS benchmark. So then the question is, after the migration, did you really do it? Like, did you solve the goal? And if you can see here, we actually did it. So we just did a final like benchmark to close all the discussions with Java. So first of all, we shadowed production traffic to 2 identical Java clusters. And as you can see, the numbers are already there. It's like 2.4x faster and better success rate, better reliability. Also on the below graph, you can see that the yellow line, the Java cluster was peaking at like 90% utilization, whereas Velox could run even more. So that's what we've been working on. Maybe in future, we can also improve the Velox utilization by squeezing out everything we can and doing more. So yeah, so for closing the final gap, I think the next presentation is already going to talk about it. But yeah, our goal is clear. We want to stop all the retries. So right now, if you saw in slide 1, we still have some data read spent in retries. So we are going to like stop that. That includes implementing some UDFs, which is left, some long tail and crash issues. Also, I think Kafka and MySQL connector are going to be important for us. So we actually have a lot of queries on Kafka. Users use Presto to quickly debug and see if their Kafka has some issues. So, I mean, Kafka push and pull has some issues. So that's what we're going to be working on. And yeah, that's it. Open for any Q&A.
Okay, in this talk, it's like a similar talk before, but this one is the Prestissimo migration at Meta, the last mile. We'll talk about the 3-year journey of this migration, system overview and architecture of Prestissimo. We'll give a very brief discussion on that. And how did we roll out in multiple phases, and some of the concerns around correctness and how did we solve them, and how Prestissimo is different from Presto Java and Velox, and production results and pricing and lessons learned and what we are up to next. So this is a long journey. So first presentation we gave in PrestoCon 2023 which was the first production use case of Velox and Prestissimo for a Presto use case. This was for a fixed shape queries where the query shapes were not changing, and we had almost 58% hardware that was reduced, and the query growth, like 3x query growth, was supported without adding any new hardware. And this was the first use case of Prestissimo to be production in anywhere in the industry. In VeloxCon 2024, we talked about how we started the general rollout, and we showed that we had roughly 60% success rate based on count, and we have 80% success rate based on CPU. And overall success rate was around 60% across the regions. And we had done improvement on shadow testing, routing, fuzzer, and non-deterministic query handling. And that was the first general purpose batch clusters in live. And at the end of 2025, December 2025, we were able to completely shut down all Java clusters from Meta that was running for roughly 15 years. And so it's 100% in production, almost 2 to 5 times better performance in our batch fleet, 6 to 7x better performance in our interactive fleet, and Java workers are fully decommissioned. So to give some scale perspective, so it's hundreds of millions of daily queries across different regions, exabytes of data scanned daily, and we have the interactive workloads that has dashboards, data exploration for latency sensitive products that could run from milliseconds to minutes. And there is a very important batch workloads which runs ETL pipelines, periodic jobs which could run minutes to hours. And there is Presto and Spark to even larger batch queries that can run up to 72 hours, which has persistent shuffle. And Presto is geographically distributed in most of the regions where warehouse lives at Meta. And there we have a Presto gateway on top of all these to route the queries. Why Prestissimo? So we started Prestissimo with the main idea of composability because we have many engines at Meta and we want kind of unified results, unified optimizations, and you want to use Velox in everywhere, Presto, Spark, streaming, ML training, and many future cases. And Presto specifically was suffering a problem from JVM because of the scale. We had GC pauses, unpredictable memory tuning, nightmares, and we had to restart the server to keep them alive. And the infrastructure mismatch, most of the Meta infrastructure, almost everything is in C++. So having a Java infra running with a separate tooling is always a trouble. And we also wanted to build not just to replace and compose, but we want to build for future so that our future infrastructure could, like AI workload explosion, could go forward with the foundations we built in last 3 years. So the architecture that has been discussed many times, it's mainly the Java coordinator. It's mostly unchanged. We didn't made a lot of changes in the coordinator. The worker is completely replaced with C++ workers that is powered by Velox. And there is a strong agreement between coordinator and worker with the HTTP REST protocol. And we have a C++ sidecar in the Java coordinator to do constant folding to make sure the results and are same with Velox, and also discover more functions that Velox has that Java no longer has. So we discarded few designs, like we didn't have any hybrid execution mode. So we don't have a Java C++ combo, or we don't have a system where some workers are Java, some are C++. We wanted a very clean replacement, and we will talk later how that aligns with our future goals to make sure only supported queries could migrate to the new infrastructure. And we definitely was looking to build for long-term and future. So the first rollout, we did a very in-phase rollout, and the tricky part of this is even though this is a very big infra, we could not kind of double the capacity. That was not in the picture. So we didn't have any parallel capacity available, and the migration was done by one cluster after another, kind of continuously freeing hardware in a rolling fashion. So in very brief, we had 3 phases. The first phase, as we discussed before, was like a fixed shape of workload, which was a kind of experimentation platform that runs in Meta and that has the SQL is predictable. So we could make sure all of these were working with Velox. And the next phase was kind of a little bit more open, but still verified queries, where we verify the query and keep track of the query by hashing them, similar to what Uber just discussed. And then we route based on the verified queries. And in the last phase, we had, because we can, the third phase is kind of block list approach. In this case, we removed the verification method because that we cannot verify practically hundreds and hundreds of millions of queries. That itself will require another warehouse to verify. So we have make sure that Velox is generally correct, and only for certain part of the Velox, for example, geospatial or some functions we could block. So we made those kind of adjustment in our routing with sidecar and Velox native sidecar. And then in phase 4, we make it completely generally available, removing all Java clusters, migrating everything to new system. So apart from performance has been discussed many times in Velox. The correctness is a very tricky thing. So we have invested heavily on different layers on correctness. And that's from top layer was the Velox fuzzers, which is the randomized testing with synthetic input, and these are cheap to run and can do many trillions of operations to make sure that it works well with the stack. We have expression fuzzer, we have the aggregation fuzzers, join fuzzers, window fuzzers, and then memory and spilling fuzzers to ensure that we kind of mimic the server's concurrent multi-tenant behavior in a smaller scenario. And also in many of the fuzzers, we use both Java eval and Velox eval as side by side, and making Java a source of truth to find where things does not match with Velox, and at the same time where things are wrong in Java also. And then we use the Presto verifier that has in Presto OSS, where we also did quite a few modifications to do special changes, and we had a query bank. So in Presto verifier, we have the general approach is you write the temporary table from a query and then checksum on the columns to match with the Java control queries and the test queries. And for non-deterministic cases, we start rewriting the queries with something deterministic so that we can do the checksum. And we could validate everything without the non-deterministic function, just that function part itself, which then can be offloaded to fuzzer to make sure that, okay, the non-determinism property of the function is intact. And at the same time, we had another layer of testing, which is also end-to-end test. It's called query bank, where we have a lot of historically found queries that were created problems in our production. We kept those queries with a unique way of generating synthetic data. And then we could run our new builds with those critical kind of queries to make sure that we are not creating regression, or we are covering all the corner cases that was found in last 3-4 years. With all these three things, we could make sure the Prestissimo release can be very quick. In Java cases, we could use 2 to 3 weeks. Now we can release very quickly, like we release every week. And the rollbacks are also less, like once, twice in a month, except once, 2 times. Twice in month was in Java, but it's like almost 2 times in 6 months in Prestissimo. Now that's the general case, but with even all these things, the major difference between Prestissimo and Velox started showing up when we start going around 98%, and we already knew that that is going to come. Even the remaining 2% is thousands of daily queries. It's not like something we could say we'll not migrate or we keep Java infra. So we had to figure out a way out. Now, in these cases, there are 2 major issues. The first issue was there are bugs that make Velox and Presto Java not agree together. That could be in Velox, that could be in Presto Java, so we decided to fix them when it makes sense. For example, where NaN semantics, time zone database, like pattern matching, there are differences in Presto Java side that we just didn't decide to copy in Velox, and we know that Velox will have a different path, and we don't want to replicate everything from Java. And we took a lot of decision, a lot of thinking, and decided where we'll diverge from Java. And that was a big thing. Like for example, the libraries like regex libraries, JSON parsing libraries, floating point to strings, array sorting, and there are quite a few more where things are generally don't agree with Java and Prestissimo. So the approach was simple. We fix bugs where possible, and for intentional divergence, we identify the customers and then give alternatives and do white glove support, but don't try to copy the bugs in, or don't try to complicate Velox just for the sake of this migration. So behavior difference, one of the major differences, NaN semantics was all over the place in Presto Java. We have a small example here. Like if you run in Java around in 2025, you'll see select NaN greater than infinity will return false, meaning NaN is smaller than infinity. But if you do an array sort, then it will put the NaN at the last, showing that the NaN is larger than infinity. At the same time, if you run a select star from these values node queries, regardless of sorting order, the NaN will always be last. So this kind of create a discrepancy of what is the differentiation between NaN and infinity. And it might look a little bit nuanced, but in a exabyte scale data, these issues happen every now and then and can surface in a query in a very weird way. So we had to solve this problem. So we make sure the Java NaN semantics is up to IEEE standard, and we fixed all the Java code to make sure it matches to the standard, and we also built Velox to the same standard so that they eventually started matching. Then there is the regular expression where Java used Ioni library, which is rich in PCRE support with look-around assertions. But in Velox, we decided to go with RE2, and which guarantees linear time and fixed memory footprint, which is extremely important for a multi-tenant system that Meta operates for its scale. So that means we will break some of the, not some, quite a few of the existing queries. For example, wherever you have these what look around assertions, what smaller than, what greater than, that would not work in Prestissimo. And any pattern with look behind, look around assertions is not supported, and RE2 developed by Google has a very strong opinion around that, so they also don't want to extend this support. So, and at the same time, why we choose RE2, we considered Journey or the Boost regex for, but they have recursive backtracking, and Ioni is coming from a C++ library called Oni, which is now archived, is no longer supported. And Meta has many production incidents with Boost regex and STD regex, which prohibit any system to run with this kind of regex because of their exponential growth in memory for bad regex. It sounds corner, but it happens every now and then in our system, and it's hard to debug when it happens. So we are very opinionated to keep it in RE2 and make sure the memory footprint of the query is under control. And it's more better to have reliable than just to make it backward compatible. But then the trouble is we have to give a fixed cost of one time to migrate all the customers out of these look around assertions to different way of writing the query, which was not trivial either. JSON parsing. So JSON parsing between Java and C++, Presto Java and Velox is different, because Velox uses SIMD JSON, which is really fast and has SIMD acceleration, but the path extraction from the JSON blob is written by in Velox, but that does not match exactly or reach as the JSON path syntax that we have in Presto Java. For example, JSON path can do expression evaluation. Like you can see here some examples where price greater than 10, you can extract paths like that. And you can also have functions in there, like properties.keys, which will see the map and return the keys. But we decided not to support this kind of complex JSON parsing, which was a corner case use case inside Meta, but there was some few hundreds of use cases like this. So we gave them different alternative, and we didn't want to complicate our JSON path parsing just for supporting few use cases. Canonicalization. So Presto Java sometimes produce canonical result. Some operation will give canonical result like JSON extract, but other JSON format or other functions will not give non-canonical result. So this makes comparison of JSON extremely difficult, even if they are same. You cannot just get two JSONs and just string match because they have the different nodes are in different places. So in Velox, we make sure that they are always canonical, which also create trouble because there are customers who depend on this other behavior. And Presto Java can sometimes parse bad JSON and sometimes not. It is non-deterministic, and again, because of that, some customers have stored bad JSONs and depended on that to extract some part of them out. But we stayed opinionated and in Velox, and we didn't support any bad JSON parsing. So it will completely fail for anything that is not a valid JSON. Behavior difference in so Presto Java has use different time zone library, like Joda library, which was embedded in the JVM, but it is not updated with what we get in Velox from the system. So then there are some queries where in a daylight saving scenario for some time zones, we see result differences. So we updated Presto Java to match the recent Joda library. For Unix time ranges, we see that some cases when the value goes out of range in Java, they truncates and make the query successful. But in Velox, we decided not to do that. We fail the query if it is not in this 292M BCE and 292M CE range. It's big range, but there are data outside of this range also, which is surprising but true. And the customers also depended on the silent truncations as per Hiram's law. If something is running and there are enough users using it, so that is kind of the real behavior. So we have to make sure we migrate those things out, make sure we have found that people are writing wrong data in date fields as they didn't know that it was getting truncated. And in Velox, we decided to fail it. Timestamp precision in Presto Java from Unix time has sub-millisecond precision. C++ has full precision. There is like pattern mismatch where in Presto Java, if you have a string that has multiple lines, it will only match the first line and it will not match the second lines. So it will give wrong result. But in Velox, we figured this out and we fixed it. And we also fixed the Presto Java. But then we also need to find customers who depend on this behavior and change their wrong assumptions on the matching. Float to string conversion, even though these like a big number we convert to worker, you'll see that in C++ we have one extra digit, like in this case, this 2 before E, which in some cases cause troubles because if you make a checksum out of these columns, then it will no longer match with Java and C++. So if some customer depends on the value and checksum, their pipeline start breaking. And there is different formatting between floats, between Folly and Presto Java that needs to be addressed. And we kept this intentional divergence instead of adding a long-term take depth with practically zero marginal value. So it was really fascinating to see Hiram's law in practice because with a sufficient number of users, every observable behavior of the system will be depended on by somebody. So even if something is bad or incorrect, it's not easy to remove over time. For example, few example is this silent truncation, invalid JSON parsing, nan ordering. All of these has thousands of customers inside Meta who depended on it. And suddenly one day if we start changing them, it's not just their query fails, but the subsequent pipeline failing make a big cascading effect. So we had to really careful, find all these cases, work with customers, give them alternatives, sometimes by ourselves fix the data to make sure the migration goes smooth and we don't leave anything in the plate to run in Java. So query routing evaluation. So during this production time, we also had these 3 stages of routing. The first stage we discussed like MD5 based. So whenever we have a verified query, we keep some hash in our database, and then we based on that we do routing. The second phase we did based on the plan. If the plan has everything that we know that are valid in Velox and verified with a list that we had, then we allow them to go through. And we also have an override, because even if Velox side we have a lot of features, but we are not ready to release something. For example, geospatial was there for some time, so the plan conversion will be successful, but then we don't want to route because we have verification pending. So we had this kind of override so that even the plan is good at Velox side, we do not run it in Prestissimo. And at some point later, we just make the block list empty, which makes every query go to Prestissimo. So in nutshell, the production results for when you truly replace the entire fleet, you'll see a lot of improvement, like significantly less hardware, and we have 2 to 5 times better execution time throughout the fleet. We have freed capacity returned for other business purposes for Meta, or supplied organic growth whatever was necessary for the business. So we don't have special SSD storage needed for experimentation because we have the in-memory cache, and we could do the finer granular capacity, so we have lower barrier to add new capacity. So the reliability is also good. The error rate is roughly 1% in Java, is roughly 0.2% in Prestissimo. Out of memory errors are order of magnitude reduction. The JVM pause is completely eliminated, and worker communication failures also significantly reduced due to Proxygen server being in the Prestissimo worker, although not 100% because the coordinator is still running Jetty. So there are work going on there. So there is, and then the maintenance for restarting to make sure the worker heap memory can be cleared was also gone. The release quality improves from 2 times per month to 2 times 6 months. We have weekly release cadence, and we have 10x more increase in code change that are released every week, because Velox is under a heavy development, and we don't want to fall behind releasing the good thing that come in Velox. So So we'll talk about pricing model very shortly. So the pricing model is is a function of CPU, memory, and the host normalization. And in the first phase, we kept the price inflated so that the customer do not see the variation, even though Prestissimo is efficient. But in the second phase, we did the pricing adjustment so that customer can see they can buy more queries with the same price. So main lessons learned here is the soft backward compatibility, the testing investment, the fixed cost of composability, and understanding the query shapes helped us to prioritize. Also, the team and people management, the migration reshaped Prestissimo ownership, because now we have Velox team who owns part of it. So there is joint Prestissimo group. There is a lot of knowledge transfer between these 2 teams, and many engineers across the Meta infrastructure and open source also contributed to Prestissimo. And what's next? We have unlocked many things like vector search, further Velox integrations, AI workload onboarding, new libraries like Axiom, and the new distributed query streaming, distributed query engine with streaming and durable shuffle Excel. And the Prestissimo become the new standard for efficiency, reliability for this kind of scale analytics. Okay, thank you, everybody.
Hello. If folks are leaving, just a reminder, if you have a green lanyard, you need to return that to security, and then also find a Meta employee to escort you out, if possible. I think there's some hanging out in the back. Thanks.
Hello everyone, I'm Naveen. I work for IBM on their What's Next Data Prestissimo Velox team. I'm here with Apurva to present about the Iceberg V3 features that we have been implementing recently. So the first set of features that we go through will be default values and the row lineage feature, and that our team has been developing at IBM. And the next will be presented by Apurva, which is on the deletion vectors and a little bit of implementation details on that, and the variant and nano timestamp support that he has implemented. So the default values support has been implemented to support the schema evaluation scenario. So Iceberg V3 introduces these two values for a column, the initial default and write default. Initial default is used to fill in the default values for the rows which are already existing after a column is added, and the write default will be used to fill in the value if the value is not supplied during ingestion for this column. So we have added support for alter table add column to set the default value in Presto. This is just an example of how it works. So we've inserted two rows in the table, and then we just added a default value for the new column, and we see that the select actually fills in the values, the default values for the existing rows. And for any new rows that we insert, if we are supplying the new value, we are going to write that value instead of the default value. So the third statement shows that we have supplied the value for the new column, and then the query after that will show the value that we have supplied in the insert statement. So right now the support is there for only reading the initial default value, and writing the value using the write default is not yet supported. That will be coming soon. So the next feature is the row lineage tracking column read. Iceberg introduced row ID and last updated sequence number for row lineage tracking. Row ID is the unique identifier for a row across the life cycle, and last updated sequence number is tied to the snapshot that a row has been added or modified in. And that's how it's computed is shown on the screen. So row ID will be generally, we don't write it when we add the rows. We just compute it on the fly using the first row ID from the manifest and then the row position in the data file. But once you do modify the rows, when you're writing into a new file, you actually materialize the row IDs and last updated sequence numbers onto the disk. So this example shows that we are inserting 2 rows in 3 batches, and we see that the last updated sequence number and the row ID is appropriately read for all these rows. So I'll give it over to Apuva to present on what he has been working on.
Thank you, Naveen. Okay, so Presto currently supports V2, and it also supports V3 now, internally at least for the Java version. But when it comes to Presto Velox, where we have CPP workers, we still don't have V3 support yet. So we started working in March, and so far we have added Delta. I'll talk about what we have added, but at a high level, what's the difference between V2 and V3 is fundamentally we should know. The first biggest difference is the deletion vectors, like how deletes work in the new version. And Iceberg V2 tend to use equality and positional delete files. V3 also use files, but it's a different file. It's not a Parquet file. It's a new file format called Puffin. And inside files, we don't store row ID and row position anymore. We just store the bitmap. So that's why it's very compact. And that's why it's called roaring bitmap, because it's a super compressed format. And in terms of other major differences, the conflict resolution. So V3 introduces a notion called data sequence numbers. So every snapshot will have its unique sequence number, and that's how the conflict resolution happens. It's still optimistic concurrency control, but we have a well-defined identifier that helps facilitate that, instead of just doing metadata comparison at runtime. And there are multiple data types that have been introduced, like variant is another big one, and timestamp nano is another one. So TLDR is V3 delete metadata files are very cheap. They are 10 to 30x smaller compared to the V2. And the read lookups is big of 1. Reading from bitmap is just reading from an array. It's pretty cheap. The other difference is in V2, whenever we have mutations, whereas let's say you are setting some primary, or not the primary, some unique key to some different values, or non-unique key as well, you'll have per row, you'll have one delete file. In V3, you'll not have that. Per data file, you'll have one. So the order has changed from per row to per data file. That's the constraint for V3. So that's why you'll have lesser number of files and lesser number of storage in those files. So it's a double when it's compared to V2. So let's dive into the Puffin file format. So let's say we have this file called data1 Parquet, and inside there we have this simple bitmap. And let's suppose the row 4 is deleted, so we'll just mark it as 1. And similarly for other rows, whenever we have a new snapshot, we can keep on, per snapshot, per data file, we'll have a new Puffin file. And it has already been instrumented in Velox already. So Velox stack is is feature complete for DVs, at least. And we have open diffs for Prestissimo and Presto Java. And once this lands, hopefully within a couple of weeks, this should be a feature complete. In terms of if you do a big O of n comparisons, so equality deletes and positional deletes, those are the primary two mechanisms, as I said, in V2. Like Iceberg V2, and those were of the order of big O of n plus m. In the V3, we only have big O of n due to big O of 1 lookup in the bitmap. So it's very cheap to do deletes. And similarly, updates in the new V3 world is implemented using 2 phases. First is the marking the bitmap for the delete vector, and then we create a new data file. As you might know, files in Icebergs are immutable, so we don't change it in place. So we create a new version of a file, and in the metadata, we reference both the files. And when there is a merge on read, we just apply the deletion vector on top of the previous version. to get the new data. It's like a new set of rows. So in terms of conflict resolution, like I said, there is a new notion called a sequence number. So let's say multiple concurrent writers are trying to write, like they're reading the same table, and let's say the sequence number at that time was 5. And let's say writer A commits some like insert, and writer B is doing some delete. So should B's delete be applied on A's insert? The answer is an invariant that V3 has introduced called only like when the sequence number of the delete file is less than, the data file sequence number, if it's less than the delete file sequence number, then only the mutation is applied onto the new snapshot. Otherwise, if this invariant is not satisfied, we will not do it. And this is how the sequence number is flowing through the stack. We have made changes to both the, like Presto Java, we have like introduced sequence number there. We have wired those through to Prestissimo and used those in the Velox stack. And we support all kind of snapshot operations. So we'll be supporting like all these methods on the left side. We have like a rollback to particular snapshot. We'll also be supporting expiring a snapshot. If you want to read metadata table, these are the two like tables that are available, like table $snapshots and table $history. And if like time travel is something you care about, that will also be like you can always go back to a particular snapshot and see what were the actual data files and what were the actual values inside those data files. You can always go and read, given that they have not expired. And the second thing is we can also do this time travel query, which is pretty popular. So that is also supported. And this is an example of the snapshot lifecycle. So suppose we have an insert where we have 3 different values, and then you do a delete operation, and one value got deleted out of it. And then if you do an insert at the snapshot number 3, you will see the the values have been updated just based on because the sequence number of the data file is less than the S1 is less than S2, so data file S1, and delete bitmap S2 is less than, so it applies to the S3 as well. And in the time travel also, the reverse sequence follows. So whatever the invariant is still maintained. The next thing is the new V3 types, like variant type and the timestamp nano. And variant type is already, I have a diff for this, and it's already like an open PR on GitHub as well, which it is fully supported now. We have made, ideally variant should be mapped to var binary, but there was a discussion around open source, like multiple committers wanted it to be mapped to JSON, just because they can use existing Presto functions like JSON extract. And variant being fully compliant to JSON is something that they cared about, so that's why we decided to use JSON as the mapping type for variant. But we can still typecast to other types as well. Presto still supports a microsecond level precision. So even though we have timestamp nano available in the native Iceberg library, we still we have some lossy conversion here. But as a community, we can decide if Presto wants to support this nanosecond level precision. I think this is something we can discuss and change our code to. So like I said, the changes have been across the stack. Like it has been across Presto Java, Prestissimo, and Velox. And the planning and the parts in the planning phase happens in the first layer. All the plumbing happens there. And then the Prestissimo just converts the Presto to Velox conversion. And the Velox stack is where all the DB and the data file manipulations happen. So what's next for Iceberg v3? So we are actively rolling out as we are speaking. Like all these changes are getting pushed. And we are actively writing devs for this. And hopefully within a month at max, we should have at least a full DV support at least. And so that all your DDL, DQL, and DML operations should fully be supported. And this is the GitHub issue where both IBM and Meta are collaborating, and we can always follow the progress there. And here are some of the key contributors from IBM and Meta. Okay, yeah, thank you.
All right, we can move to a break. I think there's some coffee and snacks set up out there, and then we will resume in about a half an hour. Test, test. All right, we're going to go ahead and start our last block of sessions. For folks who may not have seen, I would just want to share a few reminders. One is if you have a green lanyard, which I see some of you do, make sure you return the lanyard to security on your way out. You will exit through 14. Tomorrow, I hope many of you, if not all of you, will be coming back to join us again through MPK 14. You'll go through the same security process, wear your badge tomorrow, and they'll just put a new sticker on it. Finally, we are hosting our conference reception at the end of this block of sessions, and we hope you all stay and enjoy some drinks and snacks and good times with the Velox crew. Okay, so with that, I am going to introduce James from Meta, who is going to be talking about GeoVelox.
That's it. Hello. Hi, I'm James Gill. I'm a software engineer here at Meta, and today I'm going to talk to you about one of my favorite subjects in the world, geospatial queries. Now, if you don't know anything about them, that's totally fine. I'll explain them. Almost nobody does. So the first question I'm going to ask or answer is, what are geospatial queries? Because most people, like I said, aren't very familiar with them. And the second question is, why would we bother bringing them to Velox? It was a lot of work. There had to be a reason. And then lastly, I'll sort of tell you how to do it. Now, throughout this, I'm going to keep it pretty high level. Geospatial can get into the weeds pretty fast, and I want to keep you awake. But I do love talking about this stuff, so if you find me later, I can talk as many hours as you want me to talk about it. But for this part, I'm going to be more focused on concepts and obstacles rather than the nitty-gritty. So what are geospatial queries? Well, to back up a bit, I joined Facebook's connectivity initiative about 10 years ago. Not quite 10, but getting pretty close. And our mission was to connect another billion people. Now, this required us to find villages that didn't have access to power and build power lines to them, to find optimal paths of fiber optic cable backbone and lay them down in Nigeria and other places, and to reduce the per-person cost of cell towers and cell service so that it was more economically viable for cell companies to expand their coverage. But to do all this, we had to answer questions like, what towns are within 5 miles of a cell tower? What houses are in the overlap of 2 or more cell towers? What villages are not within a mile of an electrical line? And many, many more. These are all queries about locations and their relationships. And queries about locations and relationships, those are geospatial queries. Now, at first, Presto did not have any geospatial capabilities. We just ran our models on our local machines, maybe a machine in the cloud, but single machines. And that meant that we couldn't solve big problems. We could only solve small problems and small little parts of problems. But in 2017, Masha, who talked earlier today, added geospatial queries to Presto. And this was a game changer to us. Like computations that we just could not do before were done in minutes. Previously intractable problems suddenly became tractable. So we use this in a variety of ways, and one of which was we produced a suite of high-quality data sets that we opened up to the world. One, which I was near and dear to my heart because I was doing it for many years, is population density, which is the highest resolution and most accurate population maps in the world. At least it was a few years ago. I haven't done it for a few years, so who knows what's happened since then. Project North Star, where we added just thousands of miles of roads to OpenStreetMaps, and OpenStreetMaps is the open source kind of alternative to Google Maps. Another thing we did was relative wealth index to understand which communities had the greatest need. We had many, many more of these. And these are all queries about locations and their relationships. So let's dive for a second into population density. Population is often measured in census tracts, which are kind of big polygons with a number of people that live in there. Now, if you don't know anything more, you kind of have to spread the people homogeneously across the polygons. You can see it's pretty chunky. It's very coarse-grained. But using some AI and some geospatial queries, we could redistribute this to like a 50-meter by 50-meter grid, right? Which just changed the game as to figuring out where people were and whenever we needed to figure this out. So, sorry, I talked a little too fast. I should let the reel play all the way. Sweet, okay. But these are more than just numbers. So in this conference, you'll hear a lot of numbers, right? You'll hear about a CPU efficiency or latency gains or numbers of machines. But speed matters, and it matters in a lot of other contexts. It can make the impossible possible. So I'm going to talk about some other numbers here. So in 2017, El Nino caused flooding in Peru, and this destroyed 115,000 homes, left 178,000 plus some people homeless. In 2018, a magnitude 7.5 earthquake hit Papua New Guinea, leaving many people not only displaced, but also without access to food. And also in 2017, Hurricane Maria hit much of the Caribbean, but also Puerto Rico, where it not only killed about 3,000 people, but it basically wiped out the entire electrical and communication infrastructure of Puerto Rico, leaving 3.5 million people without power. So in all these cases and more, we partnered with governments and relief agencies, health agencies, the Red Cross, World Food Program, using our data and our computational capabilities to help them distribute relief aid to find people in need. So I remember after the Peru floods, I worked kind of late in the night because the World Food Program needed a map of where people were, and I could do that quickly, right? And I couldn't have done that quickly 6 months before. This is all because of geospatial queries in Presto. So when Maria hit Puerto Rico, it just, as I said, it wiped out the infrastructure. Now, one of the problems is if you lose access to the phone, how do you tell people that you don't have access to the phone, right? And so while electricity and connectivity was established in some of the major population centers relatively quickly, a lot of the more remote communities didn't have that connectivity reestablished. So we were able to figure out where Facebook activity had dropped dramatically between pre-Maria and post-Maria and help people figure out which communities they needed to go to reestablish infrastructure. And so you can see the graph here that a couple weeks after Maria, there was still a lot of loss of connectivity and communications, and this steadily got better. And the graph would get better and better over time. So it wasn't a nice to have, right? This is what allowed us to get the help necessary in time. So like I said, there's a lot of numbers in this conference. You'll hear a lot about numbers, but these are the ones that I care most about. So I hope I convinced you that geospatial queries are useful. Now the next question is, why spend the effort to bring them to Velox? Well, as we migrated from the Presto Java stack to the C++ Velox stack, we had a problem that I think many people in the room that have tried this have also encountered. When you have two stacks, you got a lot of problems. One problem is just increased cost, right? We had multiple clusters in each region, and some of these clusters were kind of underutilized. The clusters had like heterogeneous machine types, so all that was kind of a really pain. Maintenance burden was real because each of the Java stack and the C++ stack had different failure modes. They had different semantics, so the operational burden was significantly higher. Dev velocity, of course, was reduced because you had to implement everything twice, and you couldn't even implement it identically, again, because there were sort of semantic differences. So the cost was real. But one of the biggest capability gaps was geospatial. Like I said, we had it in Presto Java, and we had it for several years, but we hadn't yet done that in Velox. And one of the first discussions is, should we even bring it over, right? And basically the answer is yes, we have to. We had a lot of internal and external requirements for that. Like internally, if you're a restaurant and you want to serve an ad to someone, you don't want to serve it across the country, right? You want to serve it in the town that you're located. The Ray-Ban Meta glasses need sort of contextual awareness of where you are. In Facebook Marketplace, you want to see items that are listed near you. You don't want to buy an item that's, again, thousands of miles away. And as I said before, data for good, there's all these maps that were all maps and other data sets that were very spatially located. But externally, there was a lot of demand too. IBM was one of their high-value customers. The migration was blocked because they required geospatial capabilities. Uber, as is pretty obvious, uses a lot of geospatial queries. But in general, the open source community had been asking for this since 2023 or so. But this leads us to the next problem, which is geospatial is very tricksy. It's a real pain. Anybody who's worked in it will sympathize with me. It's just kind of a different beast. There's many things that are different, one of which is a lot of properties that you take for granted don't really apply. Like you can't really hash geometries. In fact, you don't even have a good notion of equality, and we'll get into that later, but a lot of things you assume should work just like won't work with geospatial. A lot of the operations are extremely expensive and require a lot of deep domain knowledge to do appropriately. There's complex and non-intuitive standards. There's non-semantic but syntactical differences. There's numerical stability, and like a lot of these algorithms, you have to like modify the vertices of a polygon to fit a grid to deal with the numerical stability. So you have something that's not actually the same polygon, but kind of philosophically is. Edge cases are frankly kind of the norm, not super rare. So this also required kind of significant upfront development, right? If you had 90 functions, you might think, oh, we'll just throw 30 engineers for a couple weeks, and each engineer will do 3 functions, and we're done. But the problem is there's a lot of this like foundational technology that has to be done before any of those will work. And so a lot of the parts just were not parallelizable, and again, required a lot of domain expertise. So we actually had to start a full year before, and even so, we got pretty close to almost not making it. But there are many parts like the serialization, and the types, and the joins, which are just kind of single-threaded endeavors. So that's why we had to bring it and some of the initial problems. But I want to talk to you about how we brought geospatial to Velox. And I'm going to focus on 3 core concepts and 3 obstacles. Again, I'm going to keep this high level because we're just not going to have time to go into the weeds. But I would love to talk about the weeds if you want to talk about it afterwards from 4 to 7, possibly with wine. Key concept number 1, the data model. The standards specify 7 geometry types. The first is a point, and that's the easiest. It's just a location, kind of X and Y. A multi-point is not much harder. It's many points. A line string is a sequence of locations in which you're sort of mentally drawing a straight line between each location. So it's kind of a piecewise linear curve. A multi-line string, no prizes for guessing this, is many line strings. A polygon has a closed line string as kind of a shell, and it may or may not have some interior closed line strings that represent kind of holes inside the polygon. Multi-polygons are many polygons. And lastly, and most problematically, is a geometry collection, which can contain any number of all the things we've described, including geometry collections. Now, why is this a problem? This seems like nice and well-defined, and it is well-defined, sort of. But some of the things it is just missing. So geometries don't support any sorting. There's no way to say one is greater or lesser than the other. They don't support hashing. They don't even support equality. While you might think that there's some topological point set notion, like, oh, if these contain the same points, in practice, calculating that is this very expensive operation that will give false positives and false negatives. There are many reasons for this, but one of the simplest reasons for this is different representations of the exact same geometry. So we see up here a square, pretty simple square, right? One of the simplest polygons you can imagine. And it has 4 corners, but you could express this a couple ways. One way is you start in the lower left at 0, 0, and you go to the right to 1, 0, up, left, down. But just as reasonably, you could start in the lower right at 1, 0 and go up, left, down, and right. Those are the same polygons conceptually, but they're not bitwise the same, right? So if you're going to check for equality, you can't just like check if the bits are the same. And this is as simple a case as you're going to get. When you have the polygon of Siberia, which is several hundred megabytes, that gets very hard. The next thing, which again seems like it's not going to be too bad until it gets bad, is geometry UDFs. Now, if you have 2 geometries, you might want to see what is their intersection or what is their union. How far apart are they? What's their distance? What's the area of one, or the length, or the centroid, and many, many more. The problem is that the implementation of these are very complex. Numerical stability is just a constant concern. You have to constantly make choices that are not actually totally semantically kosher, but are required to actually calculate things. The actual output in many cases is underspecified, and there are just many, many edge cases. Now, we get around this by using battle-tested open source libraries. Anyone who wants to make a geometry library, it's fun for the first 3 weeks, and then the next 10 years you're chasing down edge cases and bug reports, right? So for the most part, if anybody wants to hire me to do that, I'm pretty excited to do that, but you won't get your money's worth. But there are ones that have been around for decades, and they've dealt with all this. In Java, in Presto Java, we use 2, JTS, or Java Topology Suite, and Esri is a very major GIS company, and they have an open source library in Java. And we use both of them for Presto Java. And if you really zoom out, basically what happens is you have a geometry encoded in some way as a var binary. You deserialize it. You throw it into the library. You take what comes out. Maybe it's a double because it's an area, or maybe it's another geometry because it's the intersection or something. And then you reserialize it, and you're done. So that should be easy, right? Well, there's a lot of little details, but there's a bigger problem in migration, which is there's actually no straight compatibility. Like, there's no perfectly compatible libraries for these. Now, JTS is the happy path. There's a library called Geos in C++, and it's nominally a port of JTS. The two maintainers are friends. They sort of, like if something happens in JTS, then the Geos people do it. I've worked with them for a while. They're great people, but there's just some differences between them. Just partly C++ versus Java, but also partly because, again, the standards are underspecified, so you have a lot of equivalent representations that come out of these things. Or you have things that differ by float precision or other numerical stability things. So while the general strategy for JTS was just find the equivalent geos function, sometimes that was like 3 weeks of work. But the Esri case was worse, is because Esri is a for-profit company that sells its GIS capabilities, and while the Java part is open source, the C++ source is how they make money, so they don't make that open source, so we can't just replace that. So we actually had to find geos capabilities that were as close as possible to the Esri ones. And again, sometimes that was pretty easy, and sometimes that was not. Now, the last major concept we're going to talk about is spatial joins. And now this is something I would love to talk to you about for an hour. I have about 5 more minutes, maybe 7 minutes, so I won't talk about them in detail. But if geospatial query is about locations and relationships, well, in general, joins are about relationships of the left side with the right side, right? And spatial joins are joins where the left and right side are both geometries. So examples are which roads intersect which cities, which points are contained within which polygons, which cell towers are within 10 kilometers of villages. And when most people think about joins, they think about hashable equijoins. They think about, oh, I have like t1.a equals t2.b, so I can hash them and I can distribute them, and then I can do some hash table. But you don't have hashing and you don't even have equality, right? So how do you do this? You can always fall back to nested loop joins. And that is the default, but you know, nested loop joins are not always the most efficient. So let's take a step back for a second. Joins kind of do 2 main things, right? The first thing is for a given worker, they try to find the left side rows and the right side rows that match each other, or match the predicate filter, as quickly as possible. And the second is, when you have many machines, they try to make sure that any time a left side and a right side row would match, they're on the same machine. If they're on different machines, that's not very helpful, right? The machines don't talk to each other. They'll never know that they're matched. So these are these 2 key stages of joining, which is distributing them and then executing efficiently on a single worker. Now, in the single worker case, for a hash join, you just make a hash table, right? And you hash the join key on the left side, and you look in the hash table, and you get some right side rows, and maybe you have a more complicated predicate that you evaluate, or whatever have you. And you can't do that in spatial joins. The one answer, and probably the most popular answer that we use, is something called an R tree. Now, if you don't know what an R tree is, it's a fun and amazing world. It's a data structure where, like, every year a new academic paper comes out about a new, better R tree. But the concept is very simple, which is if you start with your geometries, you draw a box around them. And if you have 2 geometries, if they intersect, then their boxes have to intersect. So if you start with geometries and boxes around them, you make a group of them, and you make a box that contains all of them. And then you make a group of those boxes and make a box around those. And you go all the way up. So you have hierarchically nested boxes until you have this one box that encloses them all. So if you have a probe side row, a probe side geometry, you grab its box and you try to intersect it with the big root box, and like that's actually just 4 float computations. That's very easy. And if it doesn't, if the top level box doesn't intersect your geometries box, then you're done. Nothing's going to intersect, right? But if it does, you recurse 1 layer down to the children. You check each child box, and each one of those that matches, you check those children boxes. You go all the way down to find the leaf geometries that might possibly match a row. So easier said than done, but that's the way you do it. But we haven't really talked about distributed joins at all. And the spoiler is, well, I won't spoil it. So you also can't distribute via hash the way you can in a hash join. And so one way you can generally distribute things, if you have the right, if it's inner or not too bad for outers, is you broadcast. And this is something that we've talked about a bunch. It's relatively conceptually easy. Each worker gets the entire build side. So if there's a probe side and a build side row, or a left side and a right side row that match, well, if every worker has every right side row, then that match is going to be on that worker. So you sort of trivially get the property you want. It's not super efficient because each worker has the entirety of the build side, and you can run into memory pressures pretty fast. The other way is you want to partition it. But geometries have a really annoying property that's not unlike vector search and a couple other things, which is a given geometry, if it's a polygon, any way you partition the world or the set, that polygon might be in multiple partitions, right? So generically, any build side or probe side row, for any partition strategy, will be in multiple workers. So now you have multiple workers. You have to dedupe any matches. If you have an outer join, just because you didn't match that worker, there might be another worker that matched, so you don't actually know if you can emit null or not. It's a real pain. Presto Java actually has partition joins, spatial joins, but they were always awkward because the shuffles are streaming in Presto, so you can't calculate statistics. If you have materialized shuffles, you can like pause for a second, calculate statistics, distribute stuff, and do it. So we had this kind of awkward but very useful partition joins in Presto Java. And we decided for round one to just skip it. The broadcast join was good enough for most of our use cases. We could fall back in other cases that were not super optimal, but were reasonable. And my personal hope is, because things like geospatial joins and also vector joins need this multi-partition concept, that's a thing that could be built into something with materialized shuffles, like potentially the materialized shuffle axle. So we actually just kind of punted on that. So we've talked about a bunch of problems and key concepts and obstacles. And to make the long story short, we did it. It took a year and a bunch of work. We made a lot of new types and serializations, 96 UDFs, like 120 PRs, internal and external, made some spatial joins. It was the last thing that was preventing Prestissimo migration. Amit was like pinging me every day, like, hey, are you done this last thing? But finally, we got it, and then we migrated everything, and then the Java code can eventually be deprecated. So that was a whirlwind tour. It wasn't very detailed. Again, ask me for any details later. I'm going to say questions, but I actually suspect we have about like 90 seconds for questions, so maybe we'll pause.
Hello. Okay. Hi, everyone. Good evening. Welcome. I'm Pramod Satya from IBM. And today I'll be talking about the work we did last year on the Velox expression optimizer. Start with an outline of the talk. First, I'll go into the motivation behind the project, what led to a dedicated expression optimizer in Velox. Then I'll go into the internals of the expression optimizer. After that, we'll look at how the optimizer enables extensibility by design. Then we'll end with a case study involving the Presto sidecar. Okay, let's start with the motivation. So last year, the Presto team at IBM, we proposed a native SPI for Presto C++ in order to close certain critical functionality gaps that we noticed in C++ and to reduce correctness issues that were resulting from having a split brain between a Java-based coordinator and C++-based workers. So I won't go into much details about the native SPI. There's a detailed RFC in Presto, but essentially the goal is to extend Presto's plugin interface to be able to customize the Presto coordinator functionality in C++ clusters. And one such customization that we wanted was an expression optimization during query planning in Presto. So the Presto planner, it optimizes expressions in order to make query execution more efficient. And previously in C++ clusters, this plan time optimization relied on a Java-based expression optimizer, and this used Presto Java's expression evaluation. And as part of the native SPI effort, we wanted to ensure that the Presto planner optimizes expressions using Velox's expression evaluation. And this is really necessary because we want to ensure consistent expression evaluation semantics during both planning and runtime. So essentially what we wanted to add is a native expression optimizer in Presto that delegates expression optimization to the Velox's expression evaluator via a sidecar process. So the sidecar process, it's just a Presto C++ worker with a few additional capabilities. And one of this capability is expression optimization. So this native expression optimizer, it should have the same capabilities as Presto's default Java-based expression optimizer. And for this reason, we wanted to bring in all of Presto Java's expression optimizations into the native expression optimizer. So we started looking at how Presto Java optimizes expressions. And we noticed that in addition to constant folding, Presto is quite aggressive when it comes to expression optimization. It uses a bunch of logical rewrites. Let's take a look at one of the examples. So here we have a sample expression tree with a nesting level of 4. This is just used for illustration. It doesn't represent an expression from any actual workload. So right off the bat, you can see that you have a 1 equals 2 here, then a 3 plus 4, and then 4 between 2 and 8. And these can all be folded. So that's what happens in the first pass. You fold these from the input. 1 equals 2 becomes false, and then 3 plus 4, 7, and the between evaluates to true here. And then again, you see that this if can be simplified as well. But here C0 and C1 are columns, so you cannot actually constant fold it. You need to infer that because the condition is false, this subtree can simplify to C1, which is what Presto does. And it simplifies this subtree to C1. This is folded to true, and then this is an invalid cast. So what Presto does is it replaces this with a fail expression. So in the second pass, this is the transformation that happens. And you now end up with a coalesce with 3 inputs, C1, null, and C1. You can get rid of null here, and C1 is a duplicate input to this in the subtree. So you can deduplicate it, and you can essentially simplify this whole thing to C1. And you can get rid of this true input to AND here. So essentially, you end up with a much more simplified expression tree with Presto. So in this example, we took a look at the coalesce and if logical rewrites that Presto does, but it has a bunch more logical rewrites that in conjunction with constant folding really optimizes your expression. So let's take a look at the conjunct expression. So let's say you have inputs that have been folded to true. Presto just prunes those inputs. And if you have any input that folds to false, it just short circuits evaluation and returns false instead. Similarly, for a disjunct, it prunes false inputs and then short circuits evaluation to true if possible. And for a coalesce expression, it deduplicates inputs, prunes nulls, and simplifies if there's a single expression remaining, as we saw in the example. And then for a switch expression, let's say you have a condition that is folded to false, so you don't have to evaluate that condition. You can just prune it from your switch expression, and that's what Presto does. And you can short circuit if the first condition that you see can be folded to true. If we saw that in an example, and for the in function, let's say the value that you're searching for in your in list is constant, but your in list has certain like variables or column references in it. So constant folding will not be able to evaluate it, but if your in list has the constant that you're looking for, inside it, you can still simplify that to true and short circuit evaluation entirely. And Presto does all of these. And what we wanted to do is bring in all these optimizations from Presto Java into Presto C++ or Velox in order to enable Velox-based expression optimization during planning in Presto. So before looking at how we brought in these optimizations by adding an expression optimizer, let's first take a look at how expression evaluation happens in Velox. So Velox provides a user-facing typed expression interface, which is the logical representation of your expression. And in Presto C++, when you convert your Presto plan fragment to an equivalent Velox plan, or the Presto row expressions are converted to Velox typed expressions as part of this plan conversion. So you end up with a Velox plan that has these typed expressions. And in order to evaluate this, Velox first compiles it into an executable expression using an expression compiler. And this is where optimizations used to happen in Velox before, such as constant folding. Let's zoom into the expression compiler a bit more and see what actually used to happen in there before. So the expression compiler, it would optimize the shapes of certain scalar functions to enable better execution. And it had a rewrite framework that was internal to the vector function module in Velox, and it wasn't really extensible outside of it. And the compiler would also constant fold expressions, but the API that it used, it would consume an executable expression and produce back a folded executable expression. So what this meant was constant folding was not extensible as well outside of the expression compiler because it was tied to an executable expression and not the user-facing Velox expression API. So to sum up, because these expression optimizations, they were entangled within the expression compiler, it was not really extensible, and this made reuse harder for components that just wanted the expression optimization semantics without actually having to evaluate the expression with Velox's expression evaluation. And we ran into this issue when working on the Presto native expression optimizer. So now we move to the new design with the expression optimizer. So the expression evaluation pipeline still looks pretty much the same. It starts with a typed expression from your Velox plan and ends at execution. But optimization is now a standalone module over typed expressions. So instead of being abstracted within expression compilation, it is now explicit and reusable with this new module. So what this does is it keeps your execution path intact, and it removes the unnecessary coupling that used to exist between optimization and compilation. So in this slide, we can see the key API contract. Optimize is the key API here, which takes in a typed expression, returns an optimized typed expression. And the expression optimizer essentially produces an artifact that you can port, and different consumers can use it. For instance, it could be used by Velox's expression evaluation, as it is today, or the Presto sidecar with the native expression optimizer, or future backends like QDF. Two parameters are kind of important here. One is the query context, which allows users to pass in query level configs like session time zone, etc. And the make fail expression parameter, it's essentially a function which allows developers to inject engine-specific failure handling semantics into the expression optimizer. So let's say a subtree fails during constant folding. You want to be able to specify how to handle that failure, and you can do that with the expression optimizer. Let's take a deeper look. Here's the behavior model for optimize. It's going to run bottom up on your expression tree. So children are optimized first. Only if all the inputs to your subtree are constant, it tries to constant fold or evaluate the subtree. If not, it is going to attempt to rewrite the subtree into an optimal form. So one thing to note here is we don't evaluate non-deterministic functions in an expression, and this is to preserve deterministic consistency. What happens if constant folding fails for any subtree with a user level error. Say your expression contains a trivial error like divide by 0. So the optimizer, it allows you to catch such errors and inject custom error handling policy through the make fail expression parameter that we looked at before. So essentially, this gives you a practical mechanism to preserve the expression type and semantics in the face of failures. And all of this happens without blocking optimization of the rest of your expression tree. So summing up, Optimize is a deterministic API. It starts with a post-order traversal of the tree, folds eligible subtrees, rewrites otherwise. And these invariants, they allow developers to focus on the actual expression rewrite or the expression transformation logic without having to worry about the internals of how the optimizer is going to handle it. So the rewrite mechanism, let's take a closer look at it. So in this slide, we can see the core API surface for expression rewrites. And in order to enable these rewrites in a clean manner, we decided to add an expression rewrite registry in Velox, which provides a clean API contract. So first you have a register rewrite API. Using this, users can register custom expression rewrites, which are essentially expression transformations at the typed expression level. And the set of Presto expression optimizations that we looked at before, they're not really specific to Presto, and they're engine invariant. So the Velox expression evaluation, it actually registers these rewrites into the expression optimizer by default. And these are the rewrites for conjuncts, disjuncts, coalesce, switch, and if expressions. After that, you have the rewrite API, which is essentially going to iterate over all of the rewrites that you have registered, and then it tries to apply them in the order in which they were registered. So rewrite, it's either going to return a transformed expression or a null pointer if the conditions of the rewrite were not met. And once a matching rewrite is found, you just stop there and return the rewritten expression. And clear allows you to clear all the rewrites from the registry. So with this framework, all of your expression rewrites, they're registered centrally, and they're applied during expression optimization. And as a developer, you can easily inject any expression rewrite that you want into the optimizer, and the framework is going to ensure that the rewrites are applied in an ordered fashion, so the result is always deterministic. Let's now go back to the same expression tree that we looked at before. There's a small change. You have a user-defined function, let's say foo, over a single variable, let's say a, which returns a Boolean. And you have a rewrite register that says that if your argument is a big int, then you rewrite this to bar. It's quite trivial, but let's run with this example. And the rest of the expression tree looks pretty much the same. And we'll walk through how the Velox expression optimizer folds it in stages. So 3 plus 4 here is first going to be evaluated to 7, and this subtree is going to evaluate to true. And now when you come to the next layer, this subtree is going to be folded to true, and then the fail expression is going to apply here. Let's assume that via the make fail expression parameter, you have injected the Presto fail function. So essentially, when optimization fails for any subtree, you replace it with Presto's fail function. So what happens now is your cast expression, which is not valid, it's going to get rewritten to presto.default.fail. And then your foo function call is going to be rewritten to bar. And because we now add the and rewrite, which gets rid of your true inputs, you eventually end up with this expression tree, which is identical to what we used to get with Presto. Okay, so yeah, in this slide, we summarize the extensibility of the expression optimizer. So first, we have an expression rewrite registry, and using this allows us to define expression-to-expression transformations easily in a pluggable manner, and you can register a rewrite at any layer, and it always happens deterministically. And second, you have a fail handler hook, so you'll be able to customize failure handling during expression optimization per your engine requirements. And the third is the optimized expression is a typed expression, which is what Velox exposes externally. So it's portable across different backends. So together with all these three features, we ensure that the expression optimizer, it can handle different use cases without increasing the core complexity of the optimizer. Okay, finally, let's go back to the case study with the Presto sidecar that we looked at in the motivation section. And take a look at how the Presto native expression optimizer, it's implemented in the Presto sidecar. So first, the coordinator is going to delegate expression optimization to Presto C++ during the planning stage, and it will send over a list of Presto row expressions serialized as JSON over HTTP along this V1 expressions endpoint that we added. And the core expression optimization, the logic resides within Velox's expression optimizer. Presto C++ sidecar, it just takes care of the expression conversion logic. First from your input Presto expression to a Velox expression, and then your optimized Velox expression back to a Presto expression. And in order to enable this Presto to Velox expression round trip, we added in a Velox to Presto expression converter. And the sidecar, it's able to preserve Presto's failure handling semantics by injecting the Presto fail function into the Velox expression optimizer. And any new rewrite that you add into Velox, it becomes available immediately to the Presto planner. So an overview of the expression optimizer, the before and after. Before, optimization was buried inside the expression compiler. It was tied to a single backend, and now it's a reusable pass in its own separate component over typed expressions. And it has explicit hooks and boundaries to enable usability and extensibility. So in keeping with the core Velox design principles, this optimizer is reusable, extensible, and composable. So this was a large refactor in Velox core, and I would like to specially thank Christian Zendra from IBM for collaborating with me in making this a success. And also special thanks to Aditi and Masha for helping with code reviews. And thanks to everyone else who made this a successful community effort. Yeah, happy to take any questions.
We're gonna put the t-shirts away soon, so if you haven't grabbed a conference t-shirt, you should go get one now. And just a reminder, if you're leaving, there's a bunch of Meta employees that are standing outside this room to escort you out. So just find somebody with a Meta badge and they can take you.
Hello, everyone. I am Natasha Segal from the Presto team at Meta, and today I'm going to be talking about probabilistic data structures in Velox. So for today's agenda, we're going to start with a quick introduction into what these are and the kind of problems that it solves. And then I'm going to go into the different probabilistic structures we have in Velox. I'm going to talk about the ones that existed versus all of the new ones that we added to complete the Prestissimo migration. And I know Amit covered on the Prestissimo journey, so I'll quickly go into what it looked like for these structures and how to test functions that do not return the same results every time. Okay, so first, what are probabilistic data structures? So these answer the questions above, but with some sort of probability. So instead of the exact answer, these return it with a small approximate error. So the reasons for this, so this minor accuracy trade-off is worth it in real-life use cases when you care about memory and latency. And one thing to think about is how much memory difference is it if you want to get the exact answer versus an approximate one with a small error. So this is what it looks like for the questions in the previous slide. If you wanted the exact answer for 1 million data points, the answer would be in an order of megabytes. And then if you wanted to get the exact answer for like 1 billion data points, the answer is in gigabytes. And now if you were to use a sketch, so a sketch is the main probabilistic structure that I'll be covering in this talk. And a sketch is a compact data structure that summarizes data. And so if you see here that its size is in the kilobytes, and it always remains the same regardless of your data. So as the data grows, the sketch will remain the same smaller size. And since it's a smaller size, you can divide it into parts, build partial sketches on different machines. And then since they're small, they can be cheaply sent over the network and combined on one machine to get the final answer. Okay, now looking at the different structures. So to solve the quantiles, we've had KLL and Velox. Two of the new structures added are tdigest and qdigest. And we've also had hyperloglog. So I'm going to go into a couple of the new variants added. And these solve slightly different questions around cardinality, as well as in the space of set similarity and interesting questions about privacy. And I'm also going to go into a new version of the Bloom filter for membership problems. Okay, now for solving quantile estimation questions, such as what value is in the 95th percentile, or what percentile is a value. So KLL is a pretty standard way to solve these questions. It has strong error guarantees, and it's a good default in terms of performance and space. But we did add tdigest and qdigest for backwards compatibility with some of our Presto workloads. So just a quick introduction into what these are. So tdigest, how it works is it's a sorted list of centroids, so mean weight pairs. So you have different centroids, and you have more at the tails of a distribution rather than the middle. So this is good for solving questions around the tail end. For example, what is the accuracy at P9, or what is the value at P99? And then this compression is controllable. So you can have more centroids for more accuracy at the cost of memory. And now coming to another data structure that solves this quantile problem is qdigest. And this works slightly differently. So this is a tree structure which stores value ranges and counts. And unlike tdigest, this has a guaranteed error bound at any quantile. So you can configure the max error that you're OK with. And a lower error would give you more accuracy, but then the merge in the tree would be slower. One difference is since tdigest deals with division and averaging, right now in Velox we only support doubles, but you could add support for real, since float can be converted to double losslessly. And qdigest is working with counts, so it does support big int, and then real and double. So we just ported over whatever value types we had in Presto Java. Okay, so on the next topic of cardinality, which is for questions like how many distinct users visited a page. So hyperloglog exists, and we added a variant in Velox. So I'm going to quickly start with the definition of what hyperloglog is. So for calculating questions around how many distinct users, distinct numbers in a set, how this works is if you have a value, you hash it, and then you get a 64-bit output, and then the initial part, it decides which bucket it goes into. And in the second part, you count the leading zeros. So each bucket is storing the maximum number of leading zeros it's seen. And then you average over the buckets to get the approximate distinct count. And how this works is, if you think of like flipping a coin, you have to flip a coin a large number of times to get 10 heads in a row or 1,000 heads in a row. So you could think of 0 like flipping a coin and getting a head, if 0 is the head in this case. So what we added is P4 hyperloglog for Presto Java compatibility. And this is a dense-only format. So one quick thing into the representation. So when your number is, when the number of values is small enough, you can have a sparse mode, which is wherever there are non-zero buckets, you store that bucket index and then the value. But then as you see more values, all the hashes or all the buckets will be populated. So then you can store it in a fixed array. So now you just have to store the value, and then the bucket index is the array's position. And in this P4 hyperloglog format, this is only like the dense format. So you can extract out the minimum value. So the bucket value, to get back the value, it's essentially the minimum number, which is the baseline plus the delta per bucket. And then there's also some field for overflow, but this is unlikely. Because if you have a good hash function, then there is not as much skew. So this casts to and from HLL. If the HLL you're working with is sparse, then it's converted to a dense format first. Now building on hyperloglog, we have two interesting data structures. One is K hyperloglog. So this solves the same question, but across another dimension. So instead of just distinct counts, you're getting distinct counts per group. For example, how many distinct users does a zip code identify? And this is very useful in the privacy space because a common question is the K-anon or K-anonymity problem. So how this works is if you have, suppose, a group of users, and then there are very few users in a zip code, like less than or equal to some number K, then it is considered dangerous because you can re-identify the users if it's like a less number of users in a cluster. Fun fact, the K in K hyperloglog is not the same as the K in K anonymity. So what this K is, since we are storing the HLL per group, but as you get a lot of data, you're not able to store the HLL per group. So we only store HLLs for the K minimum hashed keys over here. And now the next data set is set digest. So this solves a cardinality problem, but more in the set space. So for example, what percentage of web users also use mobile? So this question is a set overlap question. Or if you look at how many users exist on both platforms, web and mobile, this is a set similarity question. So this uses the same data structures that you have in K hyperloglog, min hash and HLL, and together it gives you the overlap count. So as we saw, HLL is cardinality, it tells you how big a set is, and then min hash shows you how similar the two sets are. So this is done using a Jacquard index, which is the union of sets divided by the intersection. But in these two cases, we use the minimum cardinality set because this also helps with like set containment if one set fully contains another set. And similar to K hyperloglog, below a certain value, you get the exact answers. And above that, it uses these data structures to get the approximate estimates. So the next one is an interesting one, SFM sketch. So this is essentially hyperloglog. So you get the distinct users, questions like that. But if you had the HLL sketch and you deserialized it, you could get back the users. And so what SFM sketch does, it protects users' identity. So SFM stands for sketch flip merge. So for some of the bytes, some of the bits are independently flipped with a given probability. And this is controlled by a value called epsilon. So that if you have a lower epsilon, you flip more bits. So this results in more noise and stronger privacy, but at the cost of accuracy. Okay, now the last one here is not a sketch, but it's a very common probabilistic filter, which is the Bloom filter. And this is used for membership questions, such as, is a value in a set? If the answer is no, then no is always, no means no. And if the answer is yes, then it means that the value may be present in the set. So Bloom filter has existed, but last year we got a version of Bloom filter, which is called the split block Bloom filter, which is being used in a few meta production workloads. So this helps solve a problem of skipping rows that don't match a join. So how it's different is from the Bloom filter, it's just an optimized version. So the filter is split into blocks, cache size blocks, and then you can check if the bits of a value are in a block using SIMD in one operation. So this is used for dynamic filter pushdown in some meta workloads. So the example is if you have a hash join, you can push down the build side filters down to the table scan. And if the value never exists, there is no need to materialize it, and you can skip it at the IO later itself. Okay, so now on a different topic, now that we discussed a quick overview of the different data structures we added, is the testing in Prestissimo. And I know Amit covered this, but I'm going to just go quickly into some of the testing aspects that are useful for these data structures. So one is about aggregate functions. So also, as James said, geospatial functions was one of the last pieces migrated in 2025. And so are some of these data structures, like KLL, K-hyperloglog, and set digest. So some of the difficulties are when you're moving a data structure, it's not just the functions around it. You need to see how do you want to build it, how does the merging work, serializing, deserializing. And there were several aggregate functions as we're dealing with data at a scale. And with aggregate functions, you're processing many rows and returning one output. So in Presto Java, this is relatively easier because the framework handles inputs, outputs, its combinations, nulls, it iterates through rows. On Velox, there's a good framework to do this, but it's slightly more difficult because you're working with data at a lower level. With vectors, you need to handle nulls, memory tracking, etc. So this can create more bugs and there is scope for crashes. But the benefit here is you have a lot of control of the memory. You're not dependent on just garbage collection. And you can do performance optimization, like some of the SIMD optimizers discovered, shared previously. And you can also do zero copy serialization. So if you're sharing data to another operator, you don't need to use any intermediate buffers, and you can directly write to its output. So one interesting production quirk that came up when we were moving some of these probabilistic structures is the hash functions. So the hash function does matter. So Presto Java uses a different hash function from Velox. So for a prox distinct, we were able to use XXH64. This is a faster, more optimized hashing function. And since you're dealing with counts, it does not matter if the previous workloads from Presto Java used a different function. But for a proc set, since this returns HLL digest, if you don't match Presto Java, what we saw happening was there was an overinflated count. Because if you use different hash functions, then a value is assigned to different buckets, and the results were not correct. So one thing we made sure when adding these data structures are, especially in the unit tests, is if you're able to take a Java structure and successfully deserialize it using the CPP library. And also if you take a structure generated from CPP and Java, and can you merge it together and get a valid value in the expected range. So the next bit is testing. So from the CI side, we have a comprehensive fuzzer structure testing framework in Velox. This is an E2E test for correctness. So based on the seed you give, each seed generates a different inputs for functions. And these functions can be inputs for other functions, so you can get various query shapes. And it can do a lot more testing that unit tests can do. And the other thing is for meta, before going to production, we have a verifier suite that we run. So it samples the latest production workloads, and then you can run it on our control cluster, which is the Presto Java, and then test cluster, which is our new Prestissimo cluster. And then we can compare results. And this can also be used for custom testing. So if you have your own build, then you can also select which queries you want to run this exact framework on. And this was pretty useful for probabilistic data structures, because for the outputs, if you're dealing with a prox distinct counts, you you can see that the verifier suite works as expected. But when the output is like in bytes, for example, merge HLL, if you're introducing a new data structure, it helps to like quickly go through some of the results and deserialize it, check if it makes sense, if it's in the ranges. Yeah, so now going on to the fuzzer components that are relevant for these sketches. So one is the input generator. So if you had an input, like for example, an integer, it's very easy to use a random generator, get an integer in the minimum or maximum range that you're interested in, the kind of distribution that you want. But for sketches, you need to be able to generate these inputs. So for example, for T-digest, you would take a distribution of doubles, the compression value you want, and serialize it to a T-digest structure to use. And the next bit is how do you do result verification when you have approximate answers. So you cannot do like assert equals to 2 or 3, some sort of integer like that. So we have two strategies for the result verifiers for these aggregate functions from probabilistic data structures. So the two strategies are, one is verification, where you verify against an independent ground truth. For example, if you're doing a prox distinct on a set, and you know the results from count distinct, you'd expect it to be in the same, like in an acceptable range to say that a prox distinct is working as expected. And that's what we do. We do a similar thing for a prox percentile. And the second strategy is compare. So this is when you have a query, you can run it using different execution plans and then do some sort of a semantic comparison. So for example, if you have queries with T-digest, Q-digest, what you can do is you can run the same query on a single operator, or you can like create partial sketches and do a final aggregation and see if the results match. And then you can also try with and without spilling to disk. So one interesting thing over here is yeah, forgot what I was going to say. Yeah, so what's next? So right now on the meta side, we do have folks still working on T-digest. It's being used. There are new functions going on. And we're always looking for different opportunities. On the Velox, there is one issue created for countmin sketch. There is a requirement for frequency estimation. And fuzzer coverage, we're always looking to improve this testing suite. Like for SFM sketch, since you want non-determinism, maybe instead of looking at some sort of approximate values, it could be useful to check, run the same query plan, not just the same query, several times and see if the result makes sense statistically. Yeah, that's it. Thank you.
Hi, everyone. I'm Aditi Pandit. I am a software engineer at IBM working on What's Next data. And I am going to talk about table value functions in Prestismo, the Presto native engine. So in the talk, I'll quickly go over what table functions are and give some like motivating examples. Then the next part would be about the SQL syntax for table value functions. Then talk about the TVF APIs, and then go a bunch of starter TVFs that we wrote that illustrate the usage of the APIs. So what are table value functions? Table value functions return a table. And so they're another family. You can think about them as a family of functions like scalar or aggregate or window functions, but the table functions return table. They are used in the SQL from clause, and they compose as a table with the rest of the queries. Table functions are very popular extensibility in SQL. Polymorphic table functions are part of the 2016 SQL standard. These functions are available in all major query processing engines, Snowflake, BigQuery, Trino, Teradata, all have them, and they're broadly used for very diverse things, advanced statistical and ML functions, pattern recognition, model training, and federation uses like a connector. So I'll kind of go over some of these with examples. So I picked up like a bunch of popular TVFs, and these are from different SQL engines. So like there are like subtle differences in the syntax, but I basically want to like motivate, why table functions are there. So this is like a fairly sophisticated analytical table function, probably the most complex analytical function I've seen. It's called NPath from Teradata, so used for like funnel analysis, fraud detection. But the general idea is that you have a clickstream, so just a series of rows which are like log events. So what the user intends to do is that you have the clickstream, which is, so on is kind of like a table. So the input table is a clickstream partitioned by user ID, order by events. And what they want to do is so they're going to look at this page column in the clickstream, and they're going to map the value in the page column to symbols. So like if you're on the home page, it's A. If you're on checkout, it's B. If you're on purchase, it's C. And what the function is going to do is going to identify a pattern of like A followed by any symbol, followed by B, followed by any symbol, followed by C. So like a user has come in, visited the home page, browsed a bunch of items, done checkouts, and is going to do a purchase at some point in time. So it's going to recognize this in the log stream of that user ordered by time. And what are the results? The results, a bunch of things. So the user ID, when such a sequence was detected, so like valid user came in, checked out, and purchased. The number of times they were on the home page, so the number of items they actually looked at, the first time they entered, and the last time, so the purchase time that they have. So this is all that they want to do in one function. And what's amazing is that this function is very flexible. So you can take any table partitioned by user ID, like the signature is not really telling you what exactly are the columns that are going to be returned by this function. And depending on how you have invoked the function with all these different parameters, you decide in a very polymorphic way what are going to be the result columns at like query time. So this is, if I had to do this just with SQL without table functions, it would be like crazy number of joins, just never complete on a big table. So this is pretty impressive. Another like common use, this is something I picked from BigQuery Snowflake. So they have all these table functions for invoking like machine learning models in a SQL query. So again, the input is TS value from metrics, a metrics table, and they're looking at timestamps between today and like 7 days. And this function is going to, it takes this model, is going to build like the anomaly model, and based on a certain threshold that the user is sending in this, is going to identify all the outliers and return those rows back to the user. So this is also like very commonly used in infrastructure monitoring, fraud signal detection. And this is something from Trino. So Trino has this JSON extraction function, and you can pretty much say from a payload, extract all these columns with these different paths. And so depending on whatever is your column and whatever you have defined as these column paths, the query returns different columns, different times. So this query is also interesting because it didn't really specify the input table for JSON table function, but it is a join with orders. And so this is like an implicit lateral style where the orders is actually a table argument to the JSON table function. And the payload is like some column in the orders table. So these are like the sophisticated things folks want to do with table functions. And we had a bunch of advanced use cases in our in what's next data. And so that's why we went ahead with building this. So I hope that motivates why table functions are fun and interesting. And yeah, so now I'll go more into the details of how they appear in SQL queries, what are the components of a table function, and kind of go over the API that we built in Velox for it. So TVFs, in terms of SQL, TVFs can appear as tables in SQL statements. So we kind of stayed very close to what Reno has, so that like users can easily port functions over. Table denotes a table function. In this case, we have mock, system, different arguments. So this just tries to illustrate all the different kind of arguments you can have to a table function. So like table function can take tables, it can take scalars, it can take descriptors, which kind of denote columns. So in this case, there are 3 table inputs. And like window functions, you can partition and order by a table to invoke like the table function logic on a partition at a time. So in the parameters here, you see that input 1 is partitioned and ordered, input 3 is only partitioned, and input 2 is not partitioned or ordered. So, and then there is this co-partition clause which says that T1 and T3 are co-partitioned, which kind of means that we want the same values of C1 and C3 to appear together in a partition. So how is this function planned? So you're going to have the 3 tables, and 2 tables are going to be partitioned and ordered like window functions. And then there's going to be a join to put the rows with the same values of C1, C3 together, and all values of input 2 table. And so each of those partitions is going to be run like a window partition and going to execute the user logic. Some SQL concepts about TVFs. TVFs are polymorphic. So like mentioned, the function signature doesn't tell you what are the types of the tables. And so like they can be invoked with any table. And you know what are the columns, output columns of the result of the table function at query time. So like just taking this simple function, so we have this function called exclude columns, which is basically just doing like select star except, but it takes a table and it says that just remove these columns from the table. So like in the 2 invocations, right, one invocation says remove columns, clock and comment, the other one says just remove comment, and these 2 queries, although they're on the same table and the same function, they're actually going to return different columns back. So that's like the polymorphism of table functions. So table arguments, they can be tables, descriptors, scalars. So tables are just tables. They can have partition by, order by, and co-partition, like I explained before. And there's also a subtle nuance whether to prune or keep when empty. So this kind of tells a framework that even if you have an empty table, invoke the table function or not. Scalar arguments are just like literals. And descriptor arguments descriptor is a spec to tell that to identify columns and types. And that is also used by that can be used by the function to pick out some particular column in the table function. Arguments can be passed by name or passed by position. So like every argument can have a name, and your table function invocation can mix and match the order of the arguments because of the name or positional passing. So yeah, how do table functions execute? So because table functions are polymorphic, they have signatures, but the signature tells you that my table function takes 3 arguments, and those arguments are table, but it doesn't list out what are the columns of that table. So the user has to first write the signatures and register their functions in a registry, like what is done for scalar and aggregate functions. So when a SQL query comes in, depending on so when the parser sees the usage of table and sees the function name after that, it tries to match it up in the registry and gets like the signature of the table function. From that, it knows which arguments are tables, which arguments are literals, or which arguments are descriptors. It maps them correctly. And then it also participates in the statement analysis. So during statement analysis, which is basically binding every parse node in your SQL query to the relation, so to kind of say that every parse node is actually going to give me this table. So table functions also have to implement an analyze API. And this analysis API, the user provides all the parameters. So if you have table functions, it gives what are the columns of that table function. And during analysis, the function can validate the table arguments, do some calculations, and return back to the coordinator that this is the schema of the output table of the function. And post-analysis, this table function node is compiled into the query plan, and during execution, table functions are executed like other operators in the Velox plan. Because table functions can be invoked with input tables or without any tables at all, the operators could be like leaf operators, or they could appear in a pipeline. So there are two different APIs that a user can use for this kind of handling. So one is called a data processor, one is called a split processor, depending on whether it appears as a leaf or as an intermediate operator in the pipeline. So yeah, to kind of visually describe, your SQL query comes in, hits the Presto parser. The Presto parser looks up the registry, looks up the arguments, tries to map the arguments. The next, so it maps everything and creates like a table function parse node. This is sent to the statement analyzer, which is actually kind of mapping every parse node into like the relation or the columns of every node. And that statement analysis also calls the analyze API of the table function. That tells the statement analyzer what is going to be the output schema of the function. The planner then plans a table function as a join or window functions, depending on the variety of arguments that it has. There's also one fast part to just replace a table function with a table scan of a connector. So that is also one fast part that we added because many folks just tend to do that. And once the query is planned, it becomes ready for execution. And during execution, the author provides a data processor process function or split process function that operates on every partition or every split of the data. So yeah, so that means that there are a bundle of APIs. So everything is very Velox style. So you have function registration. The user has to write a register table function, which provides a name, the arguments of the function, a return spec, meaning that whether it's a generic table or if you know in advance what the schema is going to be, you can also fix the schema and give it at registration time. An analyzer function, which will be called during statement analysis, the data processor factory, so you can have a data processor or a split processor. And if you are going to process the table function as a leaf, it will have a split generator because you need to distribute the processing of your table function into units that can be executed on independently. So yeah, so in terms of the table arguments, we have an argument spec. So the argument spec tells you what's the name of the argument, whether it's required or not, what's the default value. And then because there are so many different kind of arguments, you have a scalar argument spec, a descriptor argument spec. So scalar argument tells you the type of the argument because it's a literal. The descriptor tells you the name and the types of the columns. And then a table argument specifies a table. It tells you whether this has row or partition semantics, whether to retain it or skip it if it's empty. And it also you can also specify whether it's fully passed through, because in many cases you actually want to pass through the entire table and just compute one additional column or something. And so the user has to write an analysis API, and the analysis returns to the framework what is going to be the output schema of this table function. You can also return a required columns map, which basically tells you that although you have these input tables with so many columns, I'm actually only interested in these columns in my table function for the processing. So this helps the optimizer with like projection pruning. And if you know the output schema of your table function already, it's fixed, you can return a return type. Oh no, actually return type is like the output schema. And the table function handle is like if you have pre-computing some metadata which you have computed at optimization time, but you want to give it to every worker during execution, you can put that in what is called a table function handle, which will be just sent to the runtime. So in terms of, that is all the analysis, and then the execution, you either work on a partition at a time, so you either write a data processor, which has an apply function, so you get a vector of input rows, and you return table function result, which is a status, which tells you either that it's consumed all the input or it is going to do one more round of processing. And you also return the output rows that you've generated. So there's kind of no relation, there doesn't need to be a kind of relationship between the input row and the output row. So any set of input rows could give you any set of output rows. So it's an arbitrary thing. And if your table function is being executed as a leaf, because it didn't have table arguments, it has only like descriptors and literal arguments, then it is executed with a split processor. So like a data processor, this is just going to like consume every split and generate all the rows. And in addition to the split processor, you have to give the split enumerator, which the function will use to like figure out what are the individual splits that can be executed on every worker. So like some sample TVFs that we wrote, these are really simple ones, but they illustrate the API. So the first one is sequence. So sequence takes 3 literal arguments, a start, stop, and a step. And the result of this table is going to be a single big integer column, which has values starting at start, stopping at stop, and is incremented or decremented based on the step value. So there's also a sequence function returning an array which does this, but this is just to illustrate the purposes of the API. So in this case, this function is executing as a leaf because it doesn't have input table arguments. And in order to make this efficient, your split handling will generate splits telling that like start and stop at these boundaries. And so depending on how many splits you want to generate, you can divide the interval between start and stop by the steps and like give individual splits to individual workers that will generate like that subset of values. And so the result of the sequence table function might not be ordered because of this, because different leaves have produced different parts of the sequence. And if you want to enforce order, you have to order by the result value. Another table function we wrote, this is also very simple. It's called exclude columns. So this is like select star except these columns. And this is like, this operates as an intermediate node. So it has a data processor. It has 2 inputs. One is the input table. And the second parameter is a descriptor, which tells you which columns it is that the user wants to omit. And so this table function data processor takes the input vector, drops the columns, and returns the input vector minus the columns back to as a result. This basically is very useful if you want to return nearly all columns, but if you there's another popular function that's called query. And query is like a connector function. So in this case, the user wants to run a query. And the query is actually just a literal parameter. It's like the precise query you want to run on a source system. So like what they want to do is stuff like this, like where they want to run a particular SQL query which has, so this is run on Oracle. Oracle has like a model syntax that model SQL syntax, and so this can't be executed by Presto, but the user wants to run this in a kind of federated style, and so this TVF allows you to just take a query parameter, which is like the literal query that you're going to run on source system, and it'll run this as a leaf operator and return results to the user. Yeah, so that's all I had. So this is what table function is about. So the API and implementation are all Velox, but since there's so much tie-up in terms of like the statement analysis and planner, we've kind of kept this in the Presto native execution module right now. And depending on how things evolve and how sophisticated this gets, we'll kind of look at putting it in Velox or Axiom or wherever that'll be. There are a bunch of people who worked on this. So I want to thank Michael, Shan, Prateek from IBM, Jay from Uber for reviewing all the code, and Timian for RFC discussions. So that's it. Any questions?
Well, look at us finishing 10 minutes early. It's good. I don't have much to say. I don't want to stand in the way of conference party, but thank you. We made it through day one. I hope it was really great. I think we learned a ton and a ton of content. Everything was recorded. I think it's all going to be on YouTube right now because we live streamed it. So feel free to go back and check. We will see you back tomorrow, same time, same place. Reminders again, enter through lobby 14, same place you entered today. If you have a green lanyard, make sure that you drop it off with security on your way out. We'll give you another lanyard tomorrow. And then if you're leaving, make sure you have a Meta employee with you to escort you out. But please stay, have a drink, have snacks, come hang out. That's why we're here, to hang out and chat and connect with each other, all right? So day one in the books. We'll see you tomorrow. Thank you.